Over to you, Nandini madam.
Thank you, sir. I now request the FDP coordinator, Dr. Mrs. Ranjan Bala Jain, madam, to address the audience.
Thank you, Nandini, Dr. Nandini. Am I audible?
Yes.
Okay. So, respected HOD Dr. Chandan Singh Rawat sir, Deputy HOD Mrs. Manisha Chattopadhyay ma'am, and dear participant, I am Dr. Ranjan Bala Jain, coordinator of Atal FDP on millimeter wave technologies. It gives me immense pleasure to welcome you all to the Atal Faculty Development Program on millimeter wave technologies, scheduled from 13 January to 18 January 2025. I'm happy to announce that around 145 participants have registered for this FDP from all over India, from various states such as Madhya Pradesh, Kerala, Tamil Nadu, West Bengal, Telangana, Karnataka, Uttar Pradesh, Odisha, Andhra Pradesh, Punjab, Puducherry, Gujarat, and Maharashtra. This, this FDP has been meticulously crafted to provide you with a well rounded understanding of the emerging domain of millimeter wave technologies. The objective of these programs are as follows: comprehensive understanding of millimeter wave technology. It will provide participants with in depth understanding of millimeter wave technology, covering its fundamentals, diverse applications, and associated challenges. Skill development in designing and implementing millimeter wave systems. It will equip participants with advanced knowledge and skills in designing and implementing millimeter wave systems, focusing on key aspects such as antenna design, beamforming techniques, and transceiver architectures. It will also foster a collaborative environment for participants from academia and industry, encouraging knowledge sharing and driving advancement in millimeter wave technology and its practical applications. Over the next 6 days, we will explore cutting edge advancement, key challenges, and potential application in areas such as 5G communication, radar systems, and beyond. We are privileged to have a distinguished lineup of experts from academia and researchers who will guide us through this enriching journey, offering a perfect blend of theoretical insights and research exposure. I have shared the schedule in the group. Session 1 will be taken by Professor Ghosh from IIT Indore and session 2 by Professor Ravi Gangwar from IIT ISM Dhanbad. Encourage you actively participate in the session, interact with the experts, and exchange ideas with fellow participants to maximize your learning experience. As we know that we are starting this FDP on the auspicious occasion of Lohri, Makar Sankranti, Pongal, and our festival Mahakumbh, which symbolize prosperity, knowledge, and spiritual awakening. Let the positive energy of these festivals infuse our minds, bodies, and souls as we embark on this journey of learning and exploration. Thank you for joining us. Let us embark on this exciting journey together to explore the frontiers of millimeter wave technologies. Wishing you all the very best and a productive and engaging week ahead. Thank you. Jai Hind. Keep learning and keep smiling. Thank you, thank you, thank you. Over to Nandini.
Thank you, madam. I now request our HOD, Dr. Chandan Singh Rawat sir, to officially declare the faculty development program on millimeter wave technologies open.
I hereby declare the Faculty Development Program on mmWave technologies formally open for all. Thank you.
Thank you, sir. With that, we conclude with the inauguration of the FDP. Wishing the participants and the organizers all the very best, I now hand over the session to Mrs. Aarti Sawant to guide us through the further proceedings of the program. Over to you, Mrs. Aarti Sawant.
Thank you, madam. Good evening, everyone. Good evening, everyone. It's a pleasure to welcome you all for today's session on millimeter wave technologies. I, Mrs. Aarti Sawant, Assistant Professor at Electronics and Telecommunication Department, VESET, and I will be communicating you throughout the today's session. Today's first session is about fundamentals of millimeter wave technology. Will be delivered by Dr. Saptarshi Ghosh. I take the opportunity to introduce him on this platform. He had received his BE degree in Electronics and Telecommunication Engineering from Bengal Engineering and Science University in 2009 and completed his MTech and PhD from the Department of Electrical Engineering at IIT Kanpur 2013 and 2017 respectively. After completing his postdoctoral research from Chungang University, South Korea, he had joined IIT Indore in 2018, where he is currently working as associate professor in the Department of Electrical Engineering. Dr. Ghosh and his research group are recipients of several awards and accolades, including INA Award, IEEE APS Fellowships, Young Scientist Awards, Best Paper Awards, International Travel Grants, etc. His research interests include frequency selective surface, microwave absorbers, electromagnetic metamaterial, and other periodic structures. I welcome you, sir, and I request you to take over the session. Over to you, sir. Hello, sir.
Yeah, hi. Am I audible?
Yes, yes, sir, you're audible.
Okay. So,
Over to you. Thank you.
yeah, thank you. I'm like, sorry, I joined a little bit late. So, give me 2 minutes. I'm going to start my talk. Okay. Just
Sure,
give
sure,
me
no
two
problem.
minutes. Hello, ma'am. Am I audible or my screen is visible?
Yes, sir, you're audible. And screen is also visible.
Okay. Okay. So, shall I start?
Yes, sir.
Okay. So, good evening, everyone. So, it seems that there are a very good number of participants out there. So, as the this Atal program is based on this millimeter wave technology and its different applications, let's start with the very basics about the millimeter wave technology. How this millimeter wave technology has arisen or has arisen, what is its frequency range, and what its different applications. In addition to that, I shall also can discuss about the what are the different substrates it can be using, what are the potential advantages and disadvantages of millimeter wave technology, and at the same time, I can start with that. Okay, if there are just so many different problems are there, what are the possible solutions? Also, you can think about that. Okay. So let's start with the basic part. So before going for the next present, like technical part, let me brief you about our institute and our research lab. So our institute belongs to, as you know, the name is that this is the Institute of Indian Technologies in the, belongs to it at Indore location, and we have started in close to 15 years, and our department has more or less 23, 24 faculty members in different expertise in that part. And our research group, if you can look into that part, our research group also have many students, PhDs, postdocs, MTechs, as well as BTech students. We mostly work on the antennas propagation, societies relevant work, mostly antennas and frequency electric surface absorbers. Student has also received different awards in different categories in IEEE and APS parts. Now let's come back to the introduction to the radio frequency. As few of you or most of you know that this radio frequency starts after this audio signal. On the audio is in the lower frequency, where is the radio frequency starting from the which consisting of the millimeter wave, microwave, and all those things. This starts post audio signal, and it start with this audio AM, FM signal, TV, microwaves, infrared, and all those things. In between that, among this microwave signal is more focused in between this, which starts from the 300 megahertz to 300 gigahertz. If you can look into that, and there are different bands have been already divided and this entire thing 300 megahertz to 300 gigahertz. As per the IEEE standards, it starts with the low frequency, very ultra high frequency, very high frequency, ALS, C band, etc., whereas the other standard as for the ABC, in this way nomenclature has been done. So mostly we follow this IEEE nomenclature when you are deriving any like frequency bands in our applications. So I may speak about these bands mostly. Okay. Now this entire thing is starting about the microwave and millimeter wave frequency bands. This mostly start from the 300 megahertz to 300 gigahertz. How this word microwave comes forward? Because at 300 megahertz to 3 gigahertz, if you look into that part, that wavelength is in the order of micron. And if you go higher frequency, it will be in the millimeter wave, but the wavelength will be in the millimeter wave in that part. Sorry, this in the not micro, it is in the meter or in that part, the lower frequency. And here, as you are increasing the frequency, your wavelength is getting reduced in that part. Now there is a one point is that in some books or some cases, people prefer to use the microwave from 300 megahertz to 3 gigahertz. In some cases, people prefer to use it from 300 megahertz to 30 gigahertz, like that, and the remaining part has been defined as the millimeter wave band. So we can consider either 3 or 330 gigahertz, but mostly people prefer to use the word 330 to 300 gigahertz, like that. So there are so many frequency bands are there across this, as I mentioned. So that is A, L, A, C, X, different bands are there. So as I mentioned that the lower frequency bands starting from A, L, A, C, X, they are part of the microwave bands, and most of these applications are well defined till date. Like you can talk about that mobile communication at 2.4 gigahertz. There are other type of radom applications which are in the X band, or is the airborne communication C band, and all those things. And also there are some Q band, K band is there. And if you look into that K band, and this yellow marking is mostly in that microwave frequency, if you can look into that part, where you can talk about the 30 gigahertz like that. So from that, these bands are not well very much popular to us because of so many disadvantage or the restrictions of the millimeter wave communication. But some of the band you might heard about the E band or W band or V band like that, which are mostly used particularly in the radar and somehow of the satellite communication. So some of them are used for this cloud radar communication. There is a very high frequency you'll be seeing. In the radar part is there, etc. Now note that when you're talking about the radar or when you're talking about the satellite communication, obviously it is not the only one signal is traveling from one point to another point. It is going to be the complete system consisting of several things. Now, as for example, I'm just talking about this. This is the frequency modulated continuous wave of FMCW radar. Most of this radar has been defined by or in India, some of the groups and some of the groups across the globe. But if you look into this part, you can see that there are some parts will be there, many electronic parts will be there. Now, the process is that suppose if you can talk about some communication in the lower frequency, all of you know that if you have the CGB band or the X band lower frequency signal, it can go at a far field or it can go at a very large distance. But as you move further, as you move little bit away from the higher frequency, 28 gigahertz, 38 gigahertz, or as per the E band, F band, or D band like that, signal will have the significant amount of propagation loss, path loss. That means you cannot send a signal more than maybe 100 meter or 1 meter using the millimeter wave frequency. Instead of that so many limitations, then why you are going to use this millimeter wave? It has so many advantages also. But the basic disadvantage is that you cannot send the signal at a very far away in the millimeter wave frequency band. So then what should be solution? You want to use the advantage of millimeter wave band, but you cannot send the millimeter wave frequency at a very far away. So then the solution is that we can use the different type of techniques to send the signal far away. Like we can use the array part, we can use the some lens part to increase the gain to send the signal like that. So if you look about this type of structures, you can find that this part is a one array geometry of the antenna, which will be sending the signal at a very high distance. And because of this array, the actually path loss can be compensated in that part. Similarly, if you look into the satellite communication and all those things, many phased array antennas, any radars are there. They are neither of the cases single antenna used. There may be hundred of antennas, thousand of antennas are combined together to take the advantage of the millimeter wave. At the same time, we can use this array structure to make the signal traveling in the far away. So that was the different frequency bands like that. Now let's start about before going to the basic applications. Let's start about the founder or the in that part or that said Jesse Bose. I hope that most of you know that said Jesse Bose is Indian. Generally, he has did his all these educations and all those his academic jobs in India only in Calcutta University at that time or University of Calcutta. Yeah, so at that time, with the very minimal amount of advantages or minimal amount of techniques, he has first demonstrated this millimeter wave communication system in that part. So in that millimeter wave communication system, it is close to 1895. He has demonstrated that part. And what he demonstrated, he has demonstrated the sending of the signal from one end to another end, almost 23-meter distance. Okay. So if you can understand that part, that signal is being, that means you need to make one transmitter and you need to make one receiver, and the signal has to be sent from one transmitter to receiver, and the operating frequency has been considered close to 60 gigahertz, and the distance was very large at that time if you consider the 23 meters. Okay, so this is a one replica setup placed in this Calcutta University Museum from Jesse Bose. It is not the original one, but it can be the ideal one. You can one understand. So, what is the process he has used actually? If you look into this hollow box, you may found that there is a one amount of part has come up. So this hollow box is mostly is used for becoming the transmitter. That means you need to send the signal, you need to generate the RF signal at 60 gigahertz. So there is some spark transmitter is there, which is actually sending the signal from there, and the sending signal will be coming up from there generating, and then this will be transmitting through these metal links in that part. Obviously you can understand this is one type of converting the signal from electrical to the electromagnetic wave part is that it is similar like antenna concept you can part. And when this signal is coming up from there, this will be one type of receiver you can expect. So maybe if I can so this is the one receiver. So this is the source, this is the transmitter antenna, this is the receiver antenna. And if you look from there, obviously this receiver antenna is connected with this rotor. So that can be rotate along this arc in that part. So what will happen that if you change this rotate angle of this receiver at one particular point when the line of sight is maintained, then it will be able to detect the signal. When the line of sight is not maintained, it will not be able to detect the system. So that type of system he has developed at that 1895, and obviously you are quite understand, and it is really understanding part that that time at that point there is no concept of lanes, antennas, polarizer, anything. He has developed everything from scratch in that part, and mostly he has developed this operation and he has varied this from 12 to 60 gigahertz in that part. Once the source is generated, it's moved from the transmitter, then it's received by this receiver, and then it has been detected by this detector like that. Obviously at that moment there is no concept of the network analyzer and all those things, mostly based on the signal receiving that antenna or uh, that point is going to be reflecting, showing that there is a detection of the signal. And obviously there are some actual replica you can think about that. Then again, these are the photos taken from the internet. So this spark gap has been a source, transmitter source as I mentioned, which is present inside this device. And then this is the one antenna, and this is another antenna. So obviously this is a one transmitting antenna, which is the left side with the source, signal is coming, and this is the receiver antenna, and this is the one prism which can be used for reflecting the signal. Now obviously you can think about that yeah. So now if you know that obviously the signal is coming from the transmitter TX in that part, so if that this is the transmitter TX will be there, I can put the receiver here RX, so then it can be able to detect like that. But at the same time I can put the receiver here RX, and I can make one type of device here, and this device I can make one type of prism, so that the signal will come here and then it will be getting refracted like that. You know that obviously with the medium 1, if this will be the suppose medium 1 and this is the medium 2, the signal is coming like that, and then signal will be reflected based on this incident angle theta like that. So same concept here, he has also checked the medium of reflection here. So when the signal is coming here with some angle from the transmitter, and based on the prism refractive index, it is able to detect what is the angle of the refraction, and the transmit a receiver can be placed at that same position to detect this angle. Okay, and this is the very old categories of the polarizer you can consider. In the polarizer, obviously this type of different devices has been combined together, and this type of polarizer is used to send the signal from one direction here, and then it is receiving at another direction with different polarizer. So in this way, you can also able to detect. Note that the concept word metamaterial was already not coined. It has been already coined by Professor Penry in 1996. But this type of polarizer, which has been made by J.C. Bose scientist, so that was also actually the made of multiple number of media, which is giving you some homogenized or artificial concept like that. So that means it is not a metamaterial, but the concept is very similar to the metamaterial which has been developed by scientist J.C. Bose. But anyhow, the idea what I'm trying to say is that this type of systems what he has derived, it is very much unique at that moment, and based on that, slowly Marconi and other scientists have started developing that part, and slowly microwave communication, millimeter wave communication has come into the picture. It has so many applications as I mentioned. So that in the space part, if you look into that space part, if you look into the space part, there is a remote sensing satellite and there are other telescopes are there. Mostly this type of telescope, few of you maybe know, this is the parabolic reflector type of things. Okay. So parabolic reflector, and here the signal, if you look into that part, this type, all those parabolic reflector concept are there. And all those parabolic reflector, the signal, why this we are using here, mostly we use the X band or some other type of, and here you can see that 3 millimeter wave of signal will be there, which is the wavelength. That means the frequency is close to 100 gigahertz or in that part, or 10 gigahertz, like that in that part. So concept is that again, that at this low frequency wavelength or the high frequency, obviously the signal will not be able to transmit much. So that's why, to counteract, we have to make this antenna very large. And second point is that we have to use the array. You cannot use one single antenna, you have to use multiple number of arrays. Some cases there will be hundred of arrays, some cases there will be the thousand of arrays. And when you put them properly, so then the signal from one, two, etc., multiple, these things are coming up, and all those signals are combined together to make a very far field or very pointing beam we can get in that part. So in other way, what we said about that, that millimeter wave communications can be used in the remote sensing or the outer space part. Obviously, in some cases they are also using the low frequency, but 60 gigahertz and many things are there. Medicine part, a few of you may know that it can also be used for the treatment part, in the particularly if you know that part, that the X-ray and all those high frequency. So if you go through this part, this X-ray part, and this very high frequency will be there, which will be on the very high frequency. So why this X-ray advantage is there? That X-ray can able to penetrate our flesh and body, but it cannot penetrate the bone. So from there we can see the structure of the bone like that. Similarly, our millimeter wave can able to transmit up to certain distance of our body, and you can use this for some breast cancer imaging and other parts. Like if suppose there is a one type of breast body is there, and if you can put some type of antennas, you will be the TX and RX will be there. So from their location of these antennas and the abnormalities you can determine, and from there we can go for the early detection. So that will be the very much advantageous for non-invasive measurement or detection part. In case of invasive detection, like you have to use the biopsy, that will be the very much painful as well as costly. But if you go for this medical biomedical imaging part using the millimeter wave, so then there will be non-invasive as well as a much low cost in that part. Now if you go for the telecommunication, almost like all of you know that telecommunication part is that that wireless communication of the electromagnetic part is a indispensable in the telecommunication. We are going to talk about more in the coming days or in the coming slides, but you get the idea in that part, that all those wireless communications are now based on the microwave as well as millimeter wave. Now what is the problem on the microwave? In the microwave, the frequency is the low frequency, and the low frequency, it is the bandwidth will be small, and you cannot send the signal, or you cannot send the data at a high speed. And for that, you may not be able to possible in the lower frequency. Currently, our 3G and 4G, whatever, so they are working at the 2.4 gigahertz. Okay, most of these antennas are similar like that. Now, obviously, at the 2.4 gigahertz, it is not possible sometimes that using the to send the signal in a bulk in that part. One of the options, you have to use the same frequency, so then you have to use the antenna array or maybe MIMO, etc. in that part, massive MIMO like that. But instead of massive MIMO or antenna array, what we can do is that we can slowly increase the frequency. And if you can increase the frequency from 22.4 to 24 or maybe 34 like that, so almost you can see the 10 times increase will be there, or even more than that. So then your signal will be able to transmit with a almost 10 times speed or close to that. Not exactly 10 times, but close to increasing that. So obviously you can see, that's why in the 3G, 4G, 5G, 6G, and whatever the upcoming 7G is coming up, we are slowly focusing to the higher bands. Now it is not only for the mobile communication, it can be go for the any wireless communication. Now if you look into this aircraft part also. So there also communication is happening in that part. If you look into the uh, drone communications also, they are also same thing. How these drone communications are happening up now? Obviously you know that in India there are many places where the mobile towers cannot be placed properly because of this limited access in the uh, forest, or if you can go into the high altitude area. So then how you can go for this mobile communications? You cannot put the towers also at that particular point. So then what people are trying to do is that they are trying to put some drone here, and they're trying to put some drone here like that. And if I have some mobile here, because of this drone connection, this tower can come up like that. So this is the on coverage or what in that part. Or if I can put three drone here, here any people will be there, he will be able to get connected either from any of the drones. So in that drone you can consider, so this drone will be connected through some amount of the mobile tower far away, and this drone will be connected from there, and this drone will be sending the signal to this mobile. Obviously it is not possible to put this entire tower at some remote area, but you can place the drone at that particular position, and you can go forward like that. That is one of the applications you can talk about that. And optical fiber, so I am now mostly focusing on the millimeter wave, means I'm talking about till below the terahertz, like 38 to 40 gigahertz or 86 gigahertz like that. If you go into the terahertz like the fiber optics, there will be huge amount of application will be there. But note that the fiber optics or optical signal you cannot send wirelessly, you need the internet or wired connection like that as of now. So if I can to look into the telecommunication part, mostly in the higher frequency are going. And in this telecommunication, there are several applications are coming up. One of the potential application is the known as RIS, which is known as the reconfigurable intelligence surface. The idea is that obviously at 2.4 gigahertz, you can send the signal maybe up to 1 kilometer. So suppose I am talking over phone here, or I am talking over laptop. So from my laptop, I have a Wi-Fi, and this Wi-Fi is sending my voice into the form of the wireless signal to the nearest base station. From the base station, it will be going to the nearest base station at your address, and you are able to capture it. So from one base station to another base station, maybe there is a distance of 1 kilometer. And since my voice will be mostly going to be transmitted at 2.4 gigahertz low frequency, so it can be easily transmitted up to 1.1 kilometer or beyond that. And at base station, once is reached, then base station will further amplify this signal and send it to you like that. But now forget about this 2.4 gigahertz, you look into the 40 gigahertz or 24 gigahertz like that. What will happen in that case? It cannot travel up to 1 kilometer. You cannot put that antenna or the base station up to 1 kilometer apart. So there will be two opportunity. One opportunity is the option alternative. One alternative is that you have to increase the amplitude or the gain of the antenna so much it can even go up to 1 kilometer, but that is very much difficult for a normal mobile or maybe with the laptop part. For this type of cases, I can send the signal up to 1 kilometer, 10 kilometer, 15 kilometer. But it is extremely difficult of integrating this system into my mobile or into my laptop. So from laptop, if I put some 40 gigahertz of antenna in my laptop, that laptop antenna is not able to transmit 1 kilometer distance. It can only be able to transmit 100 meter or 50 meter or 200 meter. So then what will be solution in that case? There this type of RIS type of solution has come up. What this RIS taking is that suppose my mobile is there, and my mobile from the signal is there, it will not go to the base station, it might go to the some RIS, which is a one periodic geometry, and it will reflect this towards the base station like that. It is one type of passive geometry which will be reflect the signal intelligently to a particular location instead of sending it to all the direction. So in this way, this RIS has also come up, and this is coming up to cater the need of the millimeter wave applications only. So at the 80 gigahertz, 40 gigahertz, or maybe close to 1 terahertz gigahertz, you cannot send the signal up beyond 100 meters or like that. So then this RIS of type of concept has come up, which can able to help this millimeter wave communication like that. In a similar way, this RIS is also planned to install this drone part, so that this RIS will get the signal from this base station, and then it will be able to communicate with this mobile antenna which is present in remote area like that. So in other way, not only about the mobile communication, you talk about the any about the IoT communication, wireless communication, everywhere that type of RIS or similar type of IRS or amount of things are going to come. So millimeter wave communication or the telecommunication has some problem at the millimeter wave, but also the solution are now being developed by this researcher also. Second thing or the third point I should say about the security screening is another application of the millimeter wave. Now, as I mentioned earlier, that our X-ray part, this X-ray radiation, it can completely up to go up to our body and it can pass through our body, but it cannot pass through our bone. But X-ray has one disadvantage is that it is radiating and it is sometimes harmful. So that's why it is not preferable to go for the X-ray every time or very close like that because it has some amount of radiation effect. But on the other side, millimeter wave doesn't have any harmful radiation effect. On the other side, millimeter wave can penetrate up to certain extent of our body, but not the full one. So what people are now proposing or have been developing is that we can put some scanner about that part, and this full body scanner will be emitting the millimeter wave towards body, and it can completely detect our body, whatever the things are there concealed in our hair, clothes and everything, or maybe upper part of our body also even. So then so then it will help us to to scan the any body without directly touching in that part. Again, it is a non-invasive type of screening we can consider. At the same time, we are not going to get the direct radiation unlike the X-ray part. Similarly, there are passive imaging or active imaging in that part. So as I mentioned earlier also, that millimeter wave thing or a signal or millimeter wave frequency can able to penetrate up to certain materials, not all the materials like that. So based on that, we can detect some of the materials or by using it as sensor. Excuse me, can anyone mute yourself? Yeah.
Hello, Hariharan sir. Thank you.
Yeah. Thank you. So in the passive imaging part, so what the idea is that suppose if you have different type of materials are there and those materials are able to, you want to detect their emissivity or they have some small amount of radiation effect is there, you can detect those in terms of the millimeter wave like that. So if you look into that part, so different type of materials are there, so those materials have different type of emissivity at different frequencies, and based on this emissivity you can detect this materials or the metals in that part without detecting or without going for any detailed testing like that. And also, as I mentioned, that there is a weapon system, there are plenty of systems are there in the weapon system where people are using the millimeter wave, starting from the radars and other things. So recently I have visited the DRDO and there are plenty of people or plenty of researchers actually, scientists, they are using different type of radars at the 60 gigahertz, at the 28 gigahertz, at the 40 gigahertz. So if you look into that type of systems, the systems what they are actually doing, that type of system is that, so this is one type of reflector type of concept you can consider, or maybe radar type of concept is there which can focus the signal at a particular direction, or it can scan the signal at a wide range in that part to find that any any incoming weapon and other parts like that. Okay, similarly if you can think about some amount of ship which is traveling or sailing in the water, so inside of ship also you have to put some amount of radar which can continuously scan the area, entire area from -50 or plus 50 or -80 to +80 like that. So with those amount of scanning part also, it is highly advantageous to use the millimeter wave in that part. So there are other applications also are there, as I mentioned that part from apart from that. So as all of you know that this 5G and everything are coming up 28 gigahertz. Obviously this 5G 28 gigahertz not the only band. There are other bands are also coming up in which they are looking into that part, like 38 gigahertz also coming up in some In some country it is the 24 gigahertz, some country it is the 18 gigahertz, like that. Okay. At the same time, if you look into that part, there are other applications coming up with automotive radars. What do you mean with automotive radars? Now, as with the advent of technology, all the cars and the some part of, at least the most part of the cars are slowly becoming automatic. That means you can have the driverless car, or the some part of your driving will become automatic. Now when they become automatic, so then the distance between these cars, you can be automatically controlled to avoid some collision and all those things. So if you have to control the distance between them, what you have to do, you can put some amount of antenna in the front side of this car, and also some amount of antenna at the back side of this car or other cars, so that when this car is traveling, so from that there is some signal is coming up, and the signal is going there reflected back. Based on this distance, it can maintain the safety, that okay, how much distance should you record. Obviously it is not the antenna will only radiating the signal, it will be the complete radar part which will actually control this part in that part, along with the electronic system, like that. So most these automatic radar mostly work from the 75 to 77 gigahertz, like that, in that part. And now with this, not only the car system, I'm talking about the automatic car radars, there are other type of V2 V and the V2X communications are there. V2B communication means is the vehicle to vehicle communication, where you are communicating between this one car to another car. But now, as I'm telling you, that it is now becoming more and more automatic in the coming days. Now, if this car will be going there, and if this is the driverless car, and then if in the front side, if there are some amount of signal will be there, that means there is some amount of signal is there. By looking into that signal, this car needs to be stopped. If the signal is red, it has to pass. If this is the green, and it has to be slowed down if it is the orange, like that. Now, how it can do? This is the car or vehicle, this is another vehicle, but the signal is not a vehicle, it is a static body. That means vehicle also needs to be connected with the signal. Similarly, if there is some human body is traveling, from the human body also it needs to be checked, and in this way you have to go. So nowadays you are not only focusing to the vehicle to vehicle, you are only focusing to vehicle to anything, V2X type of things. And there are most of the cases we are using this millimeter wave communication, like that. Passive imaging, I have already told about that, and this cloud radars and this FCW is there. And terahertz imaging is in the very high frequency. Since I am mostly focusing below 1 terahertz, I am not talking about mostly this terahertz imaging part, but this biomedical imaging is somehow is the also terahertz imaging part, where we can go for the uh, non-invasive detection and all those things you can talk about in that part. Okay. Now, but the major challenges, so I told about the so many applications. Obviously, there are more plenty applications are there, starting from RIS and other parts. But obviously, the major challenges of the millimeter wave is that it it is a very high loss. Obviously, its generation of this millimeter wave is highly expensive, and propagation is also equally expensive, like that. That means if you send the millimeter wave from my mobile antenna to your mobile antenna, it cannot reach to you beyond 100 meters or 5 meters or 10 meters. It will get attenuated very heavily. So therefore, millimeter wave in the normal cases, it will be mostly sent to the some closed guide, which is not about the wireless transmission. It will be wireless, but along with the guiding structures, like that. What do you mean by the guiding structures or other in that part? So what I'm trying to say is that if suppose if the microstrip is there, the signal will be transmitting through that. All of you know how the signal is transmitting in the microwaves. So there is a one metal will be there is another metal will be there. In between signal will be transmitting through this. So some amount of signal obviously will be going in between. Some amount of signal will be lost because of this fringing field. All of you mostly know this is the microstrip line. That means this is a some amount of open area, some amount of open area will be there. So through this open area, some amount of signal will be lost. Although not mostly lost, some might be lost in that part. But what will happen if I completely close this area like that, and if I can completely close this area? So then what will happen? Signal can continuously flow with a very limited amount of propagation loss. This is known as nothing but parallel plate waveguide, right? And if I can completely close this area, that means if I can make it completely closed like that, That means all four sides are uh, metal waveguide. So then this will be the either rectangular or the circular waveguide. So there your loss or the propagation loss of the signal will be significantly reduced like that. So hence millet were mostly used for this type of waveguides. Like you can talk about this waveguides will be there microstrip line or the CPWD transmission line, or there are some group structures are there, and some in that case you can talk about that uh, iris, rectangular cavities, and all those things. One of the thing, if you remember, probably some of you know that SIW is one good concept to talk about that in the millimeter wave. I hope that there will be one expert lecture will coming out in this series who will be going to deliver you some amount of wireless communication in the SIW. But SIW is known as the substrate integrated waveguide technology, which will be using this property of the rectangular waveguide as well as a microstrip together into this SIW part. Okay, how this concept will be there, as I mentioned you, this rectangular waveguide is which will be like that rectangular waveguide. The rectangular waveguide very low loss will be there, and if it is low loss, so then you can send very high power signal also. You can send of the order of some watt signal, even not kilowatt, but at least you can send some good amount of watt signal, 50 watt, 100 watt you can send using this type of waveguide. But in the microstrip signal or the CPW, they have the major problem is that it is a low power handling capacity. You cannot send like 50 watt, 100 watt, 200 watt, 1 kilowatt type of signal. It will get slowly damaged, or there will be not possible to send. So microstrip channel has the two problems. One is that it has a high amount of not high, it has some amount of finite propagation loss and low power handling capacity. But it has on the other side is rectangular waveguide has the advantages on that part. It can send or it can be able to communicate with the good power handling capacity as well as the minimum power handling. But if you look into these structures and these structures, the advantage of the CPW is that it can be low cost as well as easily heavily fabricated using because of this 2D. 2D means is that although it is three-dimensional, but it can be easily fabricated using the PCB technique. You can simply consider one dielectric substrate here, and you can take about this metal pattern, and you can make amount of some amount of etching here using the PCB etching, and you can make the pattern here. Similarly, here also double side cladded will be there. This is a single side cladded. So microstrip or CPWD, this type of lines are two-dimensional geometry using the PCB etching. On the other side, rectangular waveguide although have so many advantages, you cannot make it in the PCB. You can only need the metallic 3D printing concept, or you need the some metal concept like that. So it is a 3D concept with the little bit more fabrication costly like that. On the other side, this SIW or substrate integrated waveguide is the in between the two things, which is actually one 2D geometry will be there, and SIW will be 2D geometry, where if there will be amount of some amount of holes you have to put here, and in this between these holes will be there, and there will be some transmission line. So what will happen, these holes will be there. So these holes will be actually the waveguide in the horizontal direction, which will be not allowed to send the signal outside. On the other side, signal will be only able to send along this propagation direction. So SIW will help us to make the signal propagating in a particular direction with minimum loss. It can have a good power handling capacity, not like this, but at least good, better than the much microstrip. At the same time, it can be fabricated using the PCB technique like that in that part, and the fabrication cost is low. So that's why for millimeter wave cases, we mostly prefer to use the SIW technique to as a guiding structures rather than using the microstrip or CPWD line like that. Obviously, in some cases, you can use the rectangular waveguide or this type of other waveguide also. But these waveguides you cannot integrate with the on-chip mechanism, or you cannot also use this type of waveguide in a 2D surface like that. So that's why this type of structures are okay when you have to send the signal in three-dimensional, but when you need to send the signal in a circuit board, like if I talk about the cloud radar, some radar circuit will be there which is made on chip or maybe PCB. So then always we prefer to use, or mostly prefer to use this SIW type of structures for transmitting the signal across this structure like that. Okay. Now, as I mentioned you earlier, just few minutes back also, that this has the advantage of the disadvantage of the loss Disadvantage of the power handling in that microstrip part is that part. But and the fabrication will be difficult here, but here fabrication will be easier. So you have to take care about the SIW structure you can consider. And depending on if you use this depending on that, what type of receiver or transmitter you need to make. Like now, what I'm talking about, these are the actually only the transmitting device. That means if you are sending the signal or if you are so if you are generating the signal at this particular point, then signal will be transmitting. But how to generate the signal? That is also another difficulty in the millimeter wave frequency. If you, because in the microwave frequency you can easily generate the frequency in the klystron or gyraton or in that device are there. Many microwave sources are there. Sample practical application is the microwave oven. In the microwave oven, we have a microwave source, and the source will be generating the signal. The signal will be actually making the food warm. But in the terahertz, it will be very difficult to generate the signal at the terahertz. So that's what terahertz, I should say about the terahertz, about the transmitter or the detector or the source will be highly costly and are difficult. So what people are doing is that case, many people what they use that they use some microwave source in that part. So there are some amount of microwave source, and after that they use some mixer, and this mixer will actually use that modulate, make the signal modulated to make the terahertz. That means maybe I have the 10 gigahertz signal will be there as a microwave source, and then this 10 gigahertz signal we use in the super heterodyne receiver or some amount of transmitter where it will be getting amplified, or the frequency will be amplified, and it will be converted to the some terahertz or maybe high frequency, and then it will be transmitted using some SIW signal and like that. Once it will be transmitted that, again at this particular end, when we receive the signal, then this receiving signal has been demodulated. It has been stepped down to the microwave frequency, and again we use the microwave detector or the microwave receiver like that. Okay, and we can go forward. So obviously in that part you can reduce the cost of this terahertz device, terahertz detection system, but obviously there will be some amount of loss or additional complexity you can expect during the up and down scaling part like that. In a similar way as I mentioned, that there is also the difficulty you can found when you're going to make some antennas like that. When you go for the microwave antennas at the low frequency, you can easily make a low frequency horn antennas or antipodal Vivaldi antennas as a feeding antenna like that. So we have this horn antenna which will be the wideband horn antennas, which will be high gain. You can use the microstrip patch antenna also, which is although narrow band. Many people are using the dipole antenna array to send the signal in it far away in that part. But all those cases, the good thing is that you can easily make this antenna. And if you want to make the microstrip patch antenna or all those things can be also make a on chip antenna also. That means microstrip patch antenna we can make in a chip, and we can also connect it with the interconnection like in that part. And off chip means is that without the chip also you can make that part. But the advantage of this antenna, the microwave, is that it can easily made at the low frequency with the lower cost like that. But if you go in the millimeter wave, first point will be that it has a very poor efficiency will be there, because this antenna cannot send the signal much high. It maybe have the good amount of gain, but it doesn't have the much amount of antenna unless you do not make the antenna array. You cannot send the signal much distance in that part, and because of this poor efficiency, obviously your antenna as independent antenna you cannot work also. So those are the things you can consider like that. Similarly, if you look into that propagation systems or the system of the terahertz, it has closer to that, so many noise figure will be there, and it has to be making the closer to the antenna, otherwise it will be much lossy and system will be there. And there are associated packaging systems will be there, which you also need to learn in that part, mostly printed circuit board and multi-chip modules, LTCT like that, etc. Now next part we are talking about the substrates. Obviously when you're talking about the millimeter wave thing, so then you cannot use normally an FR4 substrate anymore. FR4 substrates, although some of the students might know that FR4 they can use in the 40 gigahertz, 50 gigahertz also, But no, FR4 cannot be used in that high frequency, otherwise it will be extremely lossy. So FR4 can maximum use in that unless until it is absorber or other things where the loss actually is supporting part. FR4 cannot be used beyond X band or even maximum to maximum Q band like that. So if you talk about the 28 gigahertz, 38 gigahertz like that, you can only use the Rogers or Taconic or maybe FRB, whatever the lossless substrate like that. And note that whenever you are using this lossless substrate also, you have to determine their material properties properly, because those properties are also varying with the frequency like that. As for example, if you look into the attitude at 5880, so if the analysis has been done by one of the groups and you can found that epsilon value 2.2 then shifted to 2.24, the tan delta equal to 00009 then shifted to 00004. So what you can found is that here the tan delta at the 10 gigahertz it will be very small, but at the 60 gigahertz your tan delta is also almost come down to five times it will be increased like that, close to that. That means your tan delta is also not so much good in that part. But if you look into 6010, that is closer to tan delta is fine, all the epsilon will be changing. So in other way, what I'm trying to say is that the epsilon values or the tan delta values, you need to check at different frequencies before using that part. The whatever the value obtained at the 10 gigahertz, you should not directly use this in the 50 gigahertz or 60 gigahertz or 80 gigahertz. Second point is that you cannot also use the copper or the metal part also at the millimeter wave, or you cannot use the copper. Why? Because if you look into that part, why you are using the copper and most of the cases, and if you know that the mostly either most of the cases we use the copper is either 35 micron or we use the 17 micron copper like that. Okay, 1 ounce or half ounce in that part. This is the copper thickness. Most of the people are using that part. So, but why 17 micron or 35 micron? Why not some different things? Now, this is the commercial value, like all of you know in that part. But the major thing, if you look into the part, that at the 10 gigahertz signal, 10 gigahertz, if you look into the 10 gigahertz part, and if you look into the skin depth is equal to delta, which is equal to 1 by alpha. Okay. Or if it is basically 2 by omega mu sigma, you can find like that. Okay. Square root like that. So this is the skin depth of a metal in that part, and their omega is the frequency, mu is the permeability, and sigma is the conductivity. And if you can determine at 10 gigahertz, you will found that this skin depth is close to approximately it is, 4 to 5 or 6 nano micron will be there for copper material. That means that copper material, the micron is that the 4 to 5 micron will be there. Within that point, your signal, when if this is the metal will be there and the signal will be coming up here, within 4 to 5 micron, all the signal will be getting lost as per the metal property. But if you are now adding this another 10 here, or if you make it 100 gigahertz, your delta or scan delta will be significantly becoming changing in that part. Okay, and in that case it will cannot be appearing at the same point, and in that case your this value will be not in the micron, it will be changing to the nanometer, and in that nanometer it will no longer behaving as a skin depth properly. So in this you can, in other what I should say about that, that the copper is not a very good conductor at the high frequency, particularly 60 gigahertz, 70 gigahertz. It can still work up to 40 gigahertz, but 70, 80, 90 gigahertz, you cannot use the copper anymore. You have to use similar like that, either platinum or gold or similar type of things like that. So there also you have to think about the different substrates, different conductors as per your materials, and you have to accordingly design your substrate like that. Second part will also coming up is that what frequency you are going to choose. Obviously, in the millimeter wave, there is a very high amount of, I already have mentioned, there is a high amount of propagation loss, path loss. So those propagation loss, path loss doesn't happen every frequency. It has some amount of frequency, the 28 gigahertz, 20, 35, they are the good. But if you look into that 22 gigahertz in that part, there is some amount of absorption happening because of this water. Similarly, if you look into the 60 gigahertz, you found that there is a high amount of peak is coming because of this oxygen. That means in the air molecule, there is some amount of water molecules are there, water, air, oxygen molecules are there. And when you send the signal at a high frequencies, obviously at 60 gigahertz, if you send the signal, it will get absorbed by this oxygen molecule. The loss will be much more significant as compared to the other value. So that's why if you look into that part, no antenna is generally derived at 60 gigahertz or 22 gigahertz. Either 77 gigahertz, you can look into that part, or maybe 38 gigahertz or 28 gigahertz like that, where there are this type of no attenuation will be there. Obviously, with the frequency, these values will be slightly changing with the attenuation part. But one disadvantage is that although millimeter wave has a huge spectrum, broad spectrum available, among the spectrum there are many frequency bands which are actually absorbing the electromagnetic wave. So we have to get rid of, or we have to avoid those things. Second thing is that obviously that your surface rain fed is another problem. As I mentioned, rain is coming as a water molecules are there, and this rain is also creating some amount of attenuation will be there. Depending on if the rain is very fast or how much the speed of the rain, you can also have that amount of disadvantage of the propagation. Second part is that it has creating some amount of diffuse reflection, which is not happening in the microwave. What does the diffuse reflection is that? Now you know that the signal is not flowing only through the straight path, it is actually flowing through multipath propagation. That means, suppose I have one mobile is there. From my mobile, the signal is reaching to you, but it is reaching to your mobile directly? No. There are some amount of obstacle is there. So what is happening? Signal is reaching to this obstacle, then going to here, then again there is another obstacle, then again going here, and then again reaching to you. That means there is a multipath amount of propagation will be happening. So because of this multipath propagation, it will be reaching to you. Now, where it is going through this multipath propagation, in the from which obstacle it is getting reflected? It is mostly reflected from the wall or from the tree or maybe other places like that. Now, if you think about the 2.4 gigahertz at the microwave frequency band, what will happen? Or maybe you can think about the 3 gigahertz like that. So there your wavelength will be very large. Mainly you can consider about the 1 millimeter in that part. You can talk about that part. 3 gigahertz your wavelength will be 300 by 10, no, 100 millimeter, sorry, 100 millimeter will be there. So this will be close to 0.1 meter you can consider. Okay, that means it is very large like that. So what will happen? Your signal will be coming like that, and when it will be coming like that, your this surface doesn't have that amount of roughness as compared to this 100 mm. The roughness of a wall is in the order of maybe nanometer or micron. But on the other side, here the wavelength will be coming on the around 100 millimeter or maybe 0.1 meter. So therefore, the roughness is very very small as compared to the wavelength, and hence it will not create any problem, and your signal will be following the sense law. Whatever the reflection here, similarly will be transmission. Like this is the 30 degree, and it will be flowing like that. So it is known as the specular reflection, that is normal reflection following the sense law. But what is happening at the high frequency? At high frequency, maybe talk about the 2.4 ke badle mein if you take it that 24 gigahertz, or maybe you take the 240 gigahertz. What will happen? At 240 gigahertz, your wavelength will be only 1 millimeter. And if the wavelength will be 1 millimeter, then it will be very small. That means it will be almost at par, or it will be level of the non-linearity or non-uniformity of the wall. So then sometimes the signal will not flow directly in that part. There might be some amount of scattering in different direction. Because now here, if you look into this wall part, now there is so many amount of roughness in the wall is there, and your wavelength will be also small at the similar level of this roughness. So then this will not exactly move into that direction. It will be reflecting to the different direction now. That means this it creates some amount of not normal reflection, it will create some diffused reflection. The signal will getting diffused or scattered in different direction. So therefore, it will reach to you agreed, but it will reach to more number of path after traveling to more number of path after getting scattered in more and more directions like that. So your performance will be getting reduced in that part. And also, as I mentioned, obviously there is a multipath propagation will be coming up. What I told about that part. So this more and more multipath will be happening. This will cause each and every time there is a multipath propagation will be there. Your signal will be getting reduced. Its gain will be lost. It will be more and more power will be lost like that in that part. So those are the disadvantages. You can also think about that part. It has also the similar part what we talk about the line of sight in that part. So as I mentioned about that part, if you have some amount of modem or where you need to send the signal and it is my mobile, so what will happen in that case? Signal cannot go directly through this obstacle. It can go through this, some amount of reflection can happen. So that means it cannot pass through the non-line of sight. It can only go through the line of sight like that. Okay, so it cannot go like bending part or like that. But if you go for a, again, if this length, or if you can consider this gap is very small, in that case if you can consider maybe this gap is the 1 millimeter, so then what will happen? 2.4 gigahertz signal which has a very high wavelength will be there, so that can easily pass. But this low frequency 100 millimeter or the 240 gigahertz of the signal, that cannot pass through this. It has to go through the multipath. That means obviously path will be increased, loss will be more, gain will be reduced like that. Non-line of sight things will come up. And multipath fading I already mentioned in that part, so that will be coming up. But so that's why what people are trying to do, and how it is that like the solution for that part. The solution is mostly in that part, as I mentioned, it will be the RIS geometry type of things or the reconfigurable intelligence surface. One is obviously it will be the second option I should talk about. One option is that you can increase the gain by using the array, or you can use the massive MIMO type of things. Is the instead of the single antenna, you use the tens of antennas, a 10 cross 10 antenna array or 100 cross 100 antenna array, so that you can send the signal at a far away with a large scale. Alternatively, if it is not possible for us to put that type of hundreds of antenna in a small device like mobile or Wi-Fi device or Wi-Fi modem like that, so then you can use only one single antenna, but we can use this type of RIS geometry. So what RIS can do is that it can send the signal intelligently to this communication device, and it will not send the signal in the arbitrary correction. So in this way, you can control the loss of the system slightly by not sending the signal in undesired direction and only sending to the desired direction. So there, in this way, people are now focusing on putting these RIS in different places. Like it can be placed in outside of the skyscraper, it can be put inside the hospital, it can be put inside the indoor communication to improve the communication system like that. But the major idea of this RIS is that it can compensate the propagation loss or disadvantages of whatever I mentioned, like multipath propagation or the loss part, etc., by using this RIS. Obviously, it cannot compensate this atmospheric absorption part or rain fading concept, but it can at least improve the non-line of sight. It can increase the this multipath fading part and all those things. And also at the same time, there are some amount of polarization mismatch will be there, that can also be taken care by this RIS geometry like that. Further, there are a few more challenges obviously there. As you know that there is that nowadays most of us we have the simulation softwares, and all those simulation softwares are like easier to work on the uh, are requiring to derive those things. Okay. So now the major problem of that part is that suppose there is a one antenna will be there and microstrip patch antenna, I can talk about that part. So this is the microstrip patch antenna will be there. You are going to simulate this in the either in the CST or HFSS or FACO like that. Now how these softwares are working like that? The softwares are working based on either FDD method or FEM method or all those methods. Now, in this particularly method, what they are doing, they are dividing this antenna geometry into a very small number of tetrahedral elements. I'm talking about mostly in the HFSS part. where it is used in the FDTT part like that. So they are putting it mostly in that tetrahedral may, it will divide it into the infinite number of tetrahedral. Obviously, if the unit cell will be, if the patch antenna will be simple, less number of tetrahedral. If the patch will be complex like fractal patch or maybe conformal patch like that, more and more tetrahedral will be there. Now, if you're talking about the lower frequency like 2.4 gigahertz, and if you look into the 2.4 gigahertz, so this antenna size will be large. If antenna size is large, so then the discontinuity between this small part, like if the antenna and sidewise a discontinuity will be very small, or if you can consider these boundaries will be very smoothly defined between the antenna, metal patch, and the dielectric like that. So the simulation time will be less number of tetrahedral will be required. But same thing, if you can generate at the 24 gigahertz like that, so then although your antenna size will be smaller because of this scaling down, but your number of tetrahedral will be much and much larger number in that part because of the small number of change. Because this antenna will be much smaller. If this much smaller, so then obviously you need to take smaller size of the tetrahedral, and smaller size of tetrahedral means it has the very close amount of boundary between its sidewise, your complexity will be more and more increased like that. So therefore, if you are generating one single microwave patch antenna at the lower frequency, you can use a normal computer or desktop computer, you can easily simulate it, you can do it that part. But if you can talk about the millimeter wave antenna, it is extremely difficult to simulate in a normal computer thinking about antenna array. Obviously, in the millimeter wave 124 gigahertz antenna, it will be only single antenna is difficult. So then you have to make 124 gigahertz antenna array. And when you're talking about antenna array, it will be very much difficult to simulate in a normal a desktop computer. Obviously, it will take huge amount of times like that, etc. Second part, obviously, the cost part. The low frequency network analyzer, spectrum analyzer, signal generator, noise figures, everything has a lower cost. But as you move to the higher side, their cost also increases in the manifold like that. If they talk about the 6 gigahertz VNA, that might go for the 20 lakhs or the 5 lakhs or 10 lakhs. But if you go for the 67 gigahertz VNA or 110 gigahertz VNA, it might go up to some order of the crores like that in that. Now, similarly, if I talk about that physical realization, I mentioned already the fabrication challenges part, materials part, and obviously materials part. I already talked about the substrate part, like FR4 you cannot use, you have to use the Rogers, and in the metal also copper you can only use up to 40 or 45, 50 gigahertz. You cannot use in the 70 gigahertz, 80 gigahertz. You have to bring the either gold or platinum or something in that part, and fabrication challenge is also critical. Now, if the antenna size is smaller, you cannot use a normal, very simple like the PCB etching in that part, because PCB etching has a limitation up to 0.2 millimeter, sometimes 0.4 millimeter, based on the what type of chemical etching process you are using, wet etching or dry etching like that. But there are some amount of LPK machine is there where people are using the electric mechanical etching part. There you can go up to 0.1 micron, 1 millimeter like that. After that, there is some laser etching is there where you can go up to micron. But as you go from the chemical etching to mechanical etching using LPK or similar machine, or you go for the laser machine in that part, to go for the millimeter wave antennas, your fabrication cost will be going for the significantly higher. At the same time, for copper, you know the reagent for the chemical etching will be ferric chloride. That means if you have that type of geometry will be there and some amount of copper will be there, you need to etch that type of geometry. You can simply put the ferric chloride using the masking and you can easily etch out the unwanted copper. Ferric chloride is low cost, you can make it. But when you talk about the gold in that part, so the gold cannot be easily etched using the ferric chloride. You cannot do the normal conventional PCB, you have to do the chemical vapor deposition or other type of deposition part, or the maybe other type of PCB. You cannot go for the normal PCB in that part. So what I'm trying to say is that not only the material selection is difficult, your fabrication challenge is difficult. Think about the measurement, it will be further difficult in that part. Obviously, measurement thing, you cannot make that amount of 110 gigahertz thing. What mostly people done is that they make some microwave source, then they modulate it to the millimeter wave, then they test it, Then again they demodulate the signal and they can go for the detector like that. That is the one option. Otherwise it will be extremely difficult to test it at the terahertz system like that. And if you want to integrate, obviously you need to make everything either on chip or off chip. So you cannot make 1 millimeter wave antenna in one type and in the millimeter wave transmission line in other type. You have to make everything in a similar way like that. Okay. So as I'm talking about all those things, you can get to know that okay, there are so many challenges are there, as well as there are so many advantages are there, applications are also there. So now let me come back to slightly talk about that one of the millimeter wave wireless technology, which is the antenna, and slightly give you the brief overview of the history, how this wireless technology has come up in that part. So in this what I'm trying to say is that how this millimeter wave things are coming up, and this millimeter wave has an application directly in the antenna, you can go forward. So here if you look into this part, maybe in the with the earlier device at the very low frequency in the 1900 or before that, at least that time the frequency will be extremely low, 10 kilohertz, the megahertz like that. Okay. And if you look into that part at that time, mostly we have that no mobile phone will be there, mostly we have the antennas for the other cases, and then there are some telegraphs and all those things will be there. Slowly you talk about the 1950, 1970, that amount of some amount of antennas come up, and they have started using in the mobile close to 1970 around that time. But at that time only we have able to talk, voice signals are there, no amount of message or chats or in that part or images will be able to transmit. And slowly as you increase the frequency, obviously you can see the advantages. We can start from the voice to you can send the data, and then we can started talking about the voice video call, and nowadays we can send the signals in a huge amount of data, either using the 5G or 6G, like not 6G, 4G or 5G like that. And there we are using not only the single antenna, we are using with the MIMO antenna or using the antenna array, that type of things. So if you can see about that, but although there are so many challenges are there, but with these challenges also you can found the advantage in the millimeter wave. And if you look into this antenna concept also, I hope that one of the next resource person will also tell those things. But I'm trying to give you one basic idea that in lower cases, on the lower days, in the earlier days, mostly those simple antennas are coming up. But slowly, as we move forward in 2000 onwards, this more and more on-chip antennas, MIMO antennas, massive MIMOs are coming up, and those are also using the very high frequencies, particularly millimeter wave like that. If you look into this antenna array, they are using the so many number of antennas, individual antennas combined together to give the signal, signal to be sent in the high frequency. Now let's come to the advantages for in terms of the antenna. As I already mentioned you, that a particular few frequencies like the 60 gigahertz, there are some amount of loss, or maybe there are some amount of 180, there is some amount of losses. So we do not use this type of ranges where the losses are there. Otherwise, we generally use this white color or maybe the green color for amount the communication of the electromagnetic wave. Either in the 24 gigahertz subband will be much popular across the globe, like South Korea, starting from South Korea, Japan, and US, China. They have already developed on this if their own bands at those particular frequency bands in the 5G bands. India has already initiated part, but India's 5G is mostly in the lower frequency, not in the 24 or 28 gigahertz till now. In the particular, I'm talking about the mobile application. We are mostly focusing on the 6, and then now probably in the up to date in the 7 gigahertz like that, not above that part. And this advantage you can found that with this we can obviously go for the video streaming, video calling, and all those things. Mostly I'm talking about here the wireless communication. And with this wireless communication you can use either mobile or any other IoT device or any other wireless devices also. And as I told you about that part, so there are so many systems are coming up from analog to digital to 2G, 3G, and the smart antenna MIMO systems and this massive MIMO systems like that. Now, why I'm talking about this, this is another alternative you can think about with respect to the millimeter wave technology, and or maybe it can go parallel with the millimeter wave technology like that. Why? Because in the millimeter wave technology, as I mentioned, that there are so many existing challenges currently are there. Obviously, we have resolved few challenges, but still they are starting from the fabrication, there is the measurement, there is a simulation detection problems are there, and also there are like integration problems. You can also think about that part. So with the advent of technology, those challenges are now getting resolved, but we cannot wait till all the challenges getting resolved. We cannot wait till the terahertz detector will come up, and then we can use this terahertz detector in the low cost, so that every antenna can work on the, or every mobile can work on the terahertz. No, we have to think about some parallel technology which can also give us the similar amount of advantages as compared to the millimeter wave. What the millimeter wave give: high frequency, high communication, more channel communication, that can be. So that is can come up with this MIMO or massive MIMO systems like that, which is also coming in the parallel. So just giving you a one brief idea what this MIMO is going on. In MIMO, as the name is suggesting, it is telling about the multiple input or multiple output systems is there. If you send one signal in particularly, instead of one signal, you can send the multiple amount of signals in that part, and all this multiple amount of signals can send the, can communicate with the multiple transmitter to the multiple receiver, and these multiple receivers can able to detect the signal parallel, and then it will do the demodulation, decoding, and then it change from parallel to series, and then the data can be shipped like that. So instead of sending only 1 millimeter wave antenna, if you can send 10 microwave antennas, so then you may able to almost reach in the similar level of the millimeter wave antenna without going for the much costly device and like that. But the disadvantage is that your structure size or the area volume will be much more as compared to the one antenna like that. But it might be able to achieve to the signal part. How we can look into that part? Just because of this, you can look into this concept, or some of you or many of you know this theorem like that, which is known as the Shannon's channel capacity theorem. What this theorem is telling us? This theorem tells us that this is the C is known as the channel capacity. Channel means you can consider about the one transmission line is there, or maybe any of the wireless channel will be there. If this will be the TX will be there, and if this will be the RX will be there, what will be the channel from transmission to receiver? How much the capacity of this signal transmission from transmitter to receiver or receiver to transmitter like that. And this channel capacity theorem, Shannon's theorem is telling is that it is equal to the B for the bandwidth into log 2 into 1 plus S by N. S by N is the SNR ratio. Okay. S by N equal to SNR ratio. So signal to noise ratio is the finite dB, 5 dB, 100 dB like that. But you cannot make a channel noiseless. It cannot make that N equal to 0. Obviously, every channel, be it in the waveguide where there is very low path loss, or even it is optical fiber where there is a very small path loss, always there will be some amount of small loss will be there. So therefore, the signal to noise ratio will be finite, and because of that, this log 2 will be giving you some amount of value. Now, what you can look into that part, that you can increase, how to increase this channel capacity? You can increase this channel capacity by either multiply increasing plus B, or you can increase the signal to noise ratio. But obviously, signal to noise ratio is a limited term. You cannot reduce it in overnight part, or in other way, you cannot increase this channel to noise ratio very high. Then another option is that B. B means is the frequency. So this actually gives you the idea that if you increase that frequency, then your channel capacity will be increased. That means if I make the bandwidth B equal to, maybe I can talk about the 2.4 gigahertz my signal. So it can give you the 2.4 gigahertz bandwidth like that. If instead of 2.4 gigahertz, if I can talk about the 24 gigahertz, what will happen? My bandwidth will be increasing by almost 10 times. That means if I go from 2.4 to 24 gigahertz, my bandwidth will be increased almost by 10 times. And if it will 10 times increase, that means my channel can able have the capacity of almost 10 times more. That is quite great. That means if I can send the signal 1 Gbps at 1 through the channel, I can send 10 Gbps like that. But what is the next part? As I mentioned to you that 2.4 gigahertz to 24 gigahertz, already there is a difficulty. Now what we can do? Can you do from 24 to 240 gigahertz? That will be extremely challenging. 24 you can still use the metal as a copper. You can still use RTD rod like that. You can still have that horn antennas are available, you can still have the sources. But from 240 to 24, how can you go for the 240? 240 means 2.4 terahertz. To increase this from 1 Gbps to 100 Gbps, then it will be now extremely difficult. You cannot make the entire system significantly change from that part. So therefore, we can see about that. The channel capacity is saying that if I increase my frequency, operating frequency or bandwidth, it will only increase in a linear fashion from 2.4 to 5, 3 in that part. Like it will be in a linear way you can consider about that part. See, or not linear in a linear function, I should say about that part, not a exponential function like that. And it has some limitation. On the other side, if I can use, so therefore, if you look into the SNR equal to 20 dB and your bandwidth will be equal to 4 kilohertz, so then you can consider that your channel capacity will be some amount of kbps. Now, obviously, your SNR will build, if you increase this SNR in much higher, you can have only one extra bit should be there. But on the other side, what we can do in the MIMO system, if instead of that one antenna, if I can use maybe five antenna here, five antenna here, so then there will be the 5 into 5 in that part, multiple number of paths will be created. And based on this multiple parallel path, it has can be increased to the significant amount of the channel capacity. And how much it will be increased? If you talk about the single input, single output as compared to the B, it can be increased to the delta of some value, which will be going for the significant amount of approximately M into C, like that. What does that mean? That means that if your channel has a single, initially the single capacity will be show like that, and if this channel has a M number of thing, a transmitter M number of receiver will be there, so then the total channel capacity will be M times that part. Sorry. That means you do not need to change from 2.4 to 24. Sorry. You do not need to change it from 2.4 to 24. You can only need to change from 2.4 to 1 antenna to 10 antenna to 2.4. So then you can get the similar amount of channel capacity. You can get same amount of speed you can increase in that part. Your every equipment cost and everything will be same. Only your volume will be increased like that. So that is the major advantage that channel capacities come up. So that you can send from that if you increase the 6 and all those things coming up. So in that case, like there are so many antennas people have made. Like I am showing you one or two antennas in that part. So you can see there are two antennas are there which has been developed in the MIMO concept, which can increase the channel capacity. Also, if you can talk about the four systems is there, they also channel capacity will increase like that. So obviously, if you can talk about that, so then it is the only thing that we can go for the MIMO in the lower frequency. No, we can take the MIMO concept and we can also use this MIMO concept in the millimeter wave technology also. So now there are plenty of antennas has come up in the millimeter wave which have used this MIMO concept. So these are known as the millimeter wave MIMO antennas you can talk about. And those millimeter wave MIMO has used the advantage of the MIMO higher channel capacity as well as the higher bandwidth from the millimeter wave. But obviously, as I mentioned you, that there are some pros and cons of this millimeter wave, which might be little bit creating some hindrance from using this in the higher frequency like 60 gigahertz, 70 gigahertz, 80 gigahertz. But up to 28, 30 gigahertz, 38 gigahertz, this millimeter wave technology is already well developed. So many applications has come up starting from the antenna, power divider, shift mixer and radar and all those things. Okay, so I hope that more and more applications will come up in that part also. Okay, so now let's complete here today. So this is the collaborators and funding agencies in that part. So from our side, so thank you. So please let me know if you have any doubt or query in this millimeter wave. Please note that I have not gone into the much depth of the millimeter wave because this is the fundamentals I have to talk about that part. But still, if you want any in-depth questions, you let me know so that I am able to help you in that. Okay. Some questions are there. I can take these questions. If another with after that, if other people are also coming up, they are also can put the questions. So few people have asked the questions. Uh, Ravi Kumar Rayala has asked that question: is the in drone-based communication required to place the RIS? Okay, yeah. So hope that it will be visible. So let me know if you are not, if this thing is not visible. That part in the drone-based communication, to be honest, if I don't know how that I can make the drone. So in the drone, that is the one type of payload system is there. Okay, so if you know about this drone, so this drone has this type of some legs are there, and there what the idea is that this type of at the bottom of the drone we have to put this type of RIS like that. Okay, so that means it can carry the drone. It can the drone can able to carry, and obviously note that this RIS structure cannot be too heavy because drone has a limit of maybe 10 kg or something. So this it will not be too heavy. So this is currently in a research way or R&D type of things. People has not been commercialized yet, but people have started using this drone. Recently, I visited one institute and they are from few scientists from Samir. They have already started developing that RIS which can be connected to the drone, and not one drone will be helpful because in the idea is that you have one base station is there which will be far away. Now from this base station there will be one drone will be there, and there will be another drone will be there like that. So here if this RIS will be there, this RIS can send the signal to this drone type of things, and if my mobile will be there, either it can come to here or it can come to here, but mostly this RIS can be present such a way that signal will be able to come. Now obviously it is extremely difficult. Why? Because the difficulty is that this drone will not remain also stationary. It will also mobile. It will also mobile based on this location of this mobile person. If there is some a mobile is there, it will be also locate. It will be also locate. That means whatever the signal is coming from this base station to this drone in that part, so that signal has to locate this drone position. Accordingly signal has to come, and drone also needs to know the location of this mobile part or the person who is carrying this mobile. Accordingly it will send the signal in that part. In normal base station what they would do is that they send the signal everywhere. It is not about it will only send the signal to RIS or the drone, but the drone work will be there that it will take the signal which will be transmitted by this base station, then it will locate this portion of this mobile, then it will send the signal. If it cannot be located, so then what it will do is that it will send the signal to the another drone. This drone will be located, so it will send it. So it is not only the communication part, it will be also the sensing and communication. So that will be the way it will be generally happen. Okay, I hope that this will clear the doubt if someone is asking. Next, another question has come up in that part. How in wireless environment, how to create the parallel pet kind of environment? No, parallel pet is itself an wireless environment, right? If you're talking about the parallel pet, so if this is the parallel pet will be there is another parallel pet will be there. Now here you are going to give the signal here. So this signal you are giving, this is the electric signal which is coming from some RF cable like that, and you are putting another type of connector here. There also signal is going through RF, but the signal which is traveling, it is the actual wireless signal. It is not a wired signal. It is traveling between these two parallel pit. It will be traveling. So this is always wireless signal you are talking about. This is the wired signal, which is electrical signal, which is coming through the RF cable. You can consider in that part, or maybe you are using RF cable. It is also wireless signal actually, but you can still, but you can give the wired electric signal here also by some other means. You can take the electrical signal here also through some other means, but through this parallel pit, always the signal will be wireless. Okay, so RF radio frequency alternating signal will be there. Okay. How to measure the dielectric constant epsilon r? So, Sajid, there are multiple number of methods are there for measuring the dielectric constant. For the liquid thing, for the liquid or semi-solid part, there are standard waveguide, standard dielectric probe is available. That means you can put the liquid on a bottle or in a glass. Then the probe, if you can insert that in that part, so then it will directly give you the epsilon, tan delta, permeability, tan delta, permeability also. Magnetic tan delta, electric tan delta. But this can only give you for the solid, liquid and semi-solid, not for the solid part. So this is known as the dielectric probe kit. It is available with ANSYS. Other companies are also there. On the other side, if you go for the solid, mostly people use the waveguide measurement to measure the dielectric constant of the epsilon. So you have the waveguide. Inside the waveguide, you put the dielectric, and then you send the signal from one side of the waveguide. It will go through this that, and you can come out. Then you can measure the S21 and S11 measurement. From this S11, S21, you can measure this epsilon tan delta like that. This is mostly common, which is known as the Nicholson-Ross method is there. So Professor Jalil Akhtar sir from IIT Kanpur, he is very good. His research group is very good. You can go through their research papers. There you can find more and more methods. But other researchers have also done this part. This is a very common method. You can use the Nicholson-Ross method to measure the dielectricity in that part. Okay. Second thing, another question will be come up is the 6G, 7G and beyond, obviously. So now this terminology is given based on the speed or the communication technology and all those things. As I mentioned earlier, also this on 1G, 2G, there is only on 1G there is no sending of the transmission data. Only the data is there, but no image will be there. Only voice communication will be there. The 2G, there is SMS transmission is there. 3G, 4G, slowly you are sending the video, the data transmission will be there. So the how this data is being transmitted, we are using different type of modulation scheme in the communication as well as some RF scheme in the RF side. Like earlier cases, we are only sending the signal as unmodulated. Now we are using different type of modulator scheme, QPSK, BPSK, WebDM, that type of thing. We are using different type of shift keying technique, like Nakagami fading or different type of fading technique we are also using. So that is coming from the communication side, which can helpful to increase the speed communication part. Similarly, the microwave side, we can also increase the frequency from megahertz, from kilohertz to megahertz to gigahertz like that. If you increase those frequencies also, you can have the higher bandwidth and all those things. Combinedly, you can get all those things. So this is the mostly nomenclature. G for generation, that is don't have with particularly that 5G only give this, not 4G like that. But all the facilities what 5G is there will be more transmitted to the 6G, in addition to some more facilities will be coming up in the 6G like that. Okay. Yeah. Yeah, so Sain has asked another question will be that regarding the rain loss, CP polarized or the beam steering technique can be useful for minimum rain loss. Uh, CP polarization for obviously the part is that if there are some rain will be there or the rainwater will be there, you and if need to send the signal through this rainwater, then you cannot avoid this attenuation part, because rain will be actually there is some water droplets will be there. Through that water droplets your signal will be traveling like that. Okay. So there will be, I don't think that your it will be not much helpful, but obviously these two things like the CP polar, now the beam steering part, and yeah, but this thing might be helpful what you are telling, because CP polarization signal will go continuously rotating part. One is they'll X polarized, maybe Y polarized. If the signal is going in the Z direction, electric field in one direction and X, another is the Y. In this way, it will rotate. Obviously, it will further reduce in that part, but if the rain will be very high, so then it will be, I don't think that it can reduce that part. Beam steering can also help like that if the signal is, but the problem you can think about that, I need to send the signal from A to B. Now in the beam steering, I am sending the signal not from A to B, I am sending the signal from A to in different direction and to avoid the rain. So that will go through the multipath propagation path also. Okay. So obviously it both the things will be correct in that part. That one of the option is that to avoid the rain, you have to change the direction of the signal propagation part, and then it will reach to the receiver. So this, now the direction changing, you can do it either using the beam steering, or you can using the multipath propagation. You can use the CPU also somehow like that. Okay. I hope that I have answered almost all the questions. So if anyone is asking anything, let me know. Otherwise, I can also stop it here in that part. Ma'am, your voice is not audible to me. No, it is still not.
Aarti, you're not audible.
Am I audible now?
Yeah,
Yes.
that's
Yes.
Yes, ma'am.
Participants, if you have any doubt, you can post your questions in chat box as well. So there is a
Yes, there is a
question.
question, Aarti. Dekho.
Aarti, read that question.
Hello? Yes.
So the
One
question
more
is
question
coming on
is
the
there.
drone.
Under NTN, if drone is acting as relay from K band to millimeter, how it can be?
Now the part is the NTN means is the non-terrestrial. I think if I understand that part. Now the case is that drone is relaying that part from K-band to millimeter wave. I should not say that the drone is actually uh, changing the frequency in that part. Drone is only as a delay, if you can think about that. If it is sending the signal at K-band, drone is also propagating what the further sending the signal on the K-band also. If it is in the X-band, drone is not able to make it from X-band to K-band. That means the drone has to be designed for the X-band only, and it will be there. So drone has two operations. One is that drone needs to be connected for its own operation with the main base station, and the second thing is that drone has to also send the signal through RIS and other part through the mobile part. But both has to be both, like the RIS and the drone. These two things will be different, but it's preferable that this can be has happened in the same frequency. But again, the part is that the drone-based communication is still now in the infancy part. Is very in the infancy part. People are now only started developing. In India, people had not been developing, but it just started developing in that part. So I think that I should not say much about that, how much it can change the frequency. It might be able to change it by using the super heterodyne receiver and all those things in later point of time. But nowadays, people are only using the drone as a relay system, not changing the frequency or not for any other part. That kind using the RIS as a payload, that is also very much theoretical concept which you can talk about in that part. Okay.
Hello? Sir, your FD.
I think, ma'am, there is questions are already done. I think
Any
Rohit,
other
Professor
questions from
Gangwar.
participants? Otherwise, we'll proceed further. What is the basic difference between 4G and 5G? One more question, sir.
So again, as I mentioned a few minutes back in that part, so these are the generations we are giving them term based on the what I should say about that. The more and more terminology is coming up, we are improving them and we are changing their system like that. If you talk about the 1G to 2G, in 1G there is only voice signal. In the 2G we have the communication with along with the SMS data like that. In case of the 4G, whatever the speed of the communication will be there, we have improved the significantly speed of the communication by using either massive MIMO or the MIMO antennas like that instead of the single antenna like that. Okay. So in earlier cases, it will be only the 3G or 4G, or the signal is only sending and from a single antenna. But nowadays you are using the MIMO or the massive MIMO to send a huge amount of data. Now, obviously, in the 6G, we are more focusing to use RIS beamforming network to further sending the beam. Like what I'm just giving you example is that suppose I have the 5 antennas will be there, okay, and this 5 antenna will be made as a fixed 5 antenna which can send that signal only to you. Now in the 6G or in the upcoming thing, we are going to make this antenna reconfigurable so that that antenna, 5 antennas can send a signal to you, to other person, or to another person in a real time. So those are the new things: adaptive beamforming, reconfigurable beamforming. Those are the new things we are slowly adding in the upcoming G, like 6G or 7G, like that, with the existing configuration, so that overall communication will get improved, security will be improved, latency will be reduced, and eavesdropping will be much reduced, like all those, speed will be fast, like that. So those are the things we should say about that step by step improvement. There is not significant difference, but there is a some amount of key difference are there, some amount of will be there as compared to the previous generations communication. Okay. I hope that it is okay in that part. Thanks.
Okay, I guess we are done with all the questions. Any other questions, participants? Okay, so to summarize, we explored the fascinating world of millimeter waves, from their unique properties to challenges, advantages, their bands, applications, and your expertise in this area has truly deepened our knowledge, sir. Thank you very much. Uh, may I may I
Please.
request everyone to turn on their camera so that we can click a photograph of the grid? I request all the participants and speakers to turn on the camera. Yes, ma'am, we are all set. Please let me know once we are done with the picture. Yes, are we done, team?
Manisha,
You
it's
can
done.
post in the chat box as
Manisha,
well
yeah.
if we are done. Just give me a minute, sir.
Yes.
Yeah, Arti, it is done, I guess.
Okay.
Yes.
Okay. Thank you so much, sir.
Thank you, ma'am. Take care. Yeah. Bye.
Yes,
Okay,
all the
thank
participants can turn off their camera
okay. Okay, ma'am, thank you.
so that we can save the bandwidth. Okay. Can we proceed, madam, with the next session?
Ranjanbala, madam, you are on mute, madam.
Can we proceed with the next session?
Okay, ma'am.
Anuradha, please check Ravi sir has joined or not.
Sir has joined, madam.
Yeah.
Okay, fine. Thank you.
Yeah, Aarti, please proceed.
Okay, madam. Thank you. Moving ahead with the next session. I'm pretty sure all are excited to dive into the next session now. Next session of the evening is about dielectric resonator antenna, a potential radiator for 5G, 6G MIMO antenna technology by Dr. Ravi Gangwar. He received a PhD degree in electronics engineering from Indian Institute of Technology, Varanasi in 2011. He is currently working as associate professor and head of the Department of Electronics Engineering at the Indian Institute of Technology in Dhanbad. His research interests include dielectric resonator antenna, MIMO antennas, microstrip antennas, and bioelectromagnetics. He has guided 10 PhD students and 26 MTech students. He has completed an ongoing total 14 R&D projects related to dielectric resonator antenna and their applications from various funding agencies like DRDO, SERBDST, ISRO, etc. He is a recipient of the IIT SMT Ranjana Pal Memorial Award 2020 and ZS Sholapurwala Award 2023. He is a reviewer of IEEE TAF, IEEE AWPL, IEEE APM, IEEE TVT, IEEE Communication, etc. I welcome you, sir, and without any further delay, I request you to take over the session. Over to you, sir.
Yeah, thank you very much, Dr. Aarti, for this wonderful introduction. So just let me know whether my screens are visible to each and everyone or not. Is my screen is visible? Am I audible to all?
Yes, sir.
Yes, sir. Yes, sir.
Okay, so I'm just let's check whether my
Yes, sir. Your
Sir,
screen
your
is
screen.
visible.
okay, thank you. So first of all, thank you very much for inviting me to basically discuss the work which we have carried out in the last 5 years. So today I am basically going to be discuss about the antenna which is known as your dielectric resonator antennas and how we can use these antennas for the MIMO antenna technologies. That is the basic understanding about the today's discussion. And here I have given the outline of my today's discussion. First, we are going to be discuss about what is the MIMO antenna systems and what is this technology is going to be have, what the concept we are going to be discuss about their diversity, because that is the backbone of their MIMO technologies, and then how it is going to be functioning and what are the requirement of when we are going to be design the MIMO antenna systems. Then we will discuss about their DR according to his basic requirement, then introduction and some fundamentals about the electronic antennas. And then I will discuss what are the different techniques are available in the literature to basically design and improve the performance of the MIMO antenna systems. And finally, I will discuss some of our structures that we have recently published. And finally, we are going to discuss about their conclusion and the future scope. So first, I will discuss about the MIMO antenna technology. So the MIMO antenna technology is basically, if we see the current situations, then people are basically focusing on to these three major technologies, starting from your OFDMA, which is the basically your orthogonal frequency division multiple access. If I'm talking about this particular technology, then we can say that it is a multi-users version of the OFDM that can be used into your wireless communication, like Wi-Fi, 4G, LTE, and 5G systems or 5G applications. This is a technology which basically designed to improve the wireless network performance by establishing the independent modulating subcarriers within the frequencies. This technology is going to be offer the simultaneous transmission to and from the multiple clients. That is a major, we can say that the advantages of this particular technology. But when we are going to be design and implement into their system, then we find that we are facing a lot of problems with this particular technology. The problems basically associated with the implementations, interference, synchronization, resource allocation complexity, and power consumptions. Then people are basically working on this one, then they find that we can move where we can basically going to be address some of these problems. Then they got the new technology that is known as the AMC, or we can say that adaptive modulation and coding. Here we can say that this EMC is going to be give the information, or it denotes the ability to adapt the modulation scheme and the coding rate to the instantaneous quality of the radio links. So we can say that here, as the channel conditions are going to be worse, a more robust modulation and coding scheme is going to be used, where the highly efficient modulation and coding scheme is going to be used when we are going to be have the best channel conditions. So that is adaptive in nature, where we are going to be required what kind of your modulation schemes. Based on that, it is going to be switch over between your good and bad. But here again, this concept is going to be give your efficient way to increase the spectrum efficiency of their OFDM systems, or we can say that is the advanced version of their OFDM. Yes, but again, it is going to be facing from your two major problems: the power consumptions and the resource allocation complexity. The third technology that is used into your current scenarios, or we can say that is going to be grown like the Europe. Nowadays, we are discussing about their massive MIMO operations. So here we are basically going to be focused on to your two major things: multiple input and multiple output. So the multiple input means we can say that we are going to be have more than one antennas into your transmitting side and more than one antennas into your receiving side. So multiple input means more than one antenna at the transmitter side, and multiple output means more than one antenna at your receiver side. So the first thing is that why we need these multiple antennas, what the benefits we are going to be get it from here. So for that purpose, let us see the first condition, which is the most important and most general form of the communication, that is your CISO system. We have your single input, single output. That means we are going to be have the one transmitter and one receiver here. So when we are going to be check here, when my transmitter is going to be start radiating, then your signal can be choose multiple path X, Y, Z, and we can say that this is W. So here I have shown you your four different paths. From there, the transmission signal can travel and reach to your receiver. But if you see, when these signals are going to be traveling with a different route, then they will go for their different environmental conditions. And due to these environmental conditions, they are going to be face their different kind of their noise and feeding into the system. And due to this feeding, there is a problem at their receiver side. So we can say that this multipath propagation is basically creating the feeding into their system, and due to that my signal is going to be degraded. And when my signal is going to be degraded, that is my link capacity and link reliability, both are basically going to be drastically reduced. So what is the solution for this link reliability and link capacity improvement? The solution is that if we are going to be consider the multiple antennas, that is basically going to be over the feeding problem into your system. And overall, it is going to be improve the reliability of your system without requiring any additional power and spectrum. So that is the backbone of your multiple input, multiple output technologies, where we are going to be use more number of antennas into your transmitting side, more number of antennas into your receiver side to overcome the feeding problems into your multipath propagation. How we are going to be do it? So for this one, we required one simple concept, which is known as your diversity. Diversity, we can say that in the one line, if I'm going to be explain it, then I can say that combining of the independent feeding signal path. That means we are going to be combine the different faded signal path which are independent to each other. So that means indirectly I can say that we are going to be incorporate the multipath propagation in the MIMO antenna technology. But if you see in the previous slide, I have discussed that the multipath propagation is creating the basically signal degradation. But that is a problem which is this is the coming into your CISO or most fundamental communication system. But when we are going to be improve, when we are going to be converting from the CISO system to the MIMO system, then this diversity principle is going to be improved our performance. How? So here we can say that if we are going to be consider three different paths, this is my transmitter, and here I am going to be have my receiver, and my signal is traveling from one place to the another place, and there may be a three different paths. This is path 1, this is path 2, this is path 3. So my diversity principle is going to be say that if we are going to be have the three different paths, then there is always a very less probability of all the three signals are going to be fitted together. So we can say that there is always a better chance, so that at least out of three, one signal can be reached at the receiver, which is going to be suffer from the minimum fading or noise. And if my if my receiver is going to be, we can say that you're having the enough capability so that it can process that one signal and it can retrieve the maximum information. This is the basically your concept of the diversity principle. So here, by using diversity principle, we are going to be improving the signal degradation and the link performance of your overall MIMO antenna system. So how we can achieve the diversity? So there are three ways to do the diversity. The first one is a time diversity. So here we can say that a message can be transmitted at a different time, such as by using the distinct time slots and channel coding. So that is a well-known fact, and we are using this time diversity is quite long ago, even into their different kind of the systems. Then second one, we are moving towards the frequency diversity. It means this diversity utilize the different frequency spectrums. We can say that it could take the form of using different channels or technology like spread spectrum or OFDM. But we have already discussed that that is not going to be fulfill our purpose. For that one, if we want to use the diversity principle, then we need to create the multipath as much as possible, so that we are going to be have the more number of the signals, and there is always a very less probability that all the signals are going to be fed together. So we are going to be towards the this specific concept. And then we are going to be have your third mode of diversity, that is your antenna diversity. So here we can say that this is the backbone of your MIMO antenna technology. What it says that we will see one by one. So here I have discussed about your CISO system, which is the most fundamental system of the communication, that is single input, single output, where we are going to be have your one transmitting antenna and one receiving antennas. Now, when the technology evolved, then we reach at your CMOS system, where we are going to be say that single input and multiple output. That means at the transmitter side, we are going to be have their one antenna, but at the receiver side, we are going to have the more than one antennas. When this system will come into the picture, then we can say that by using this concept, we can improve the signal quality, which may be due to your special diversity, but it is basically not able to improve the data rate at so much. But the quality of signal is going to be improved. That means the reliability of the system is going to be improved. This kind of the system can be used where only the receiving side needs benefit from the special diversity, like the mobile phone receptions. Now, second one is my MISO concept. That means here we are going to be have your more numbers of antenna in the transmitter and single antenna onto the receiver side. And that is concept is known as your MISO concept, multiple input, single output. Here we can say that we can transmit the data very fast. So that means my data is going to be higher data rates. But here we are going to be have only one antenna. It means there is a lot of chance of the interferences and fading. It means here the reliability is going to be little bit down as compared to your CISO systems. But we can use this concept into the radar system where we require the focus signal transmission. So in one case, we are going to be get your good signal quality. In another case, we are going to be get your good data rate. When we are going to be combined, then we are going to be consider overall improvement into the system, and that is going to be known as your MIMO systems, where we are going to be have your multiple antennas on the transmitter side and multiple antennas on your receiver sides. So now here I have discussed about your general MIMO configuration, where we can say that we can use multiple antennas at the both source and the destination. So let us consider here I have, let us suppose 3x3 configuration I have considered. That means 3 antennas into your transmitter side and 3 antennas into your receiver side. This is 1, 2, 3 at the transmitter side. This is 1, 2, 3 at your receiver side. So now let us see. So if antenna 1 is going to be transmitted, then we are going to get your signal at antenna 1, 2 and 3 into the receiver side. If all the 3 antennas are going to be simultaneously transmitting, that means at receiver side at antenna 1 is going to be received 3 signals, which one coming from the transmitter 1, transmitter 2 antenna and transmitter 3 antenna. So at a time receiver is going to be have total 9 different signals that is coming from the 9 signals that is coming from the transmitter side. If my processor, if my receiver is having the enough processing, then it can easily detect which signal is going to be have the minimum losses or minimum fading, and by using that particular signal we are able to get the our information properly. So that is the benefit of the diversity, and that's why we are going to be go for the MIMO converter. So we can say that MIMO system is going to be offer the higher capacity, increased data rates, better coverage, low bit error, and improved position estimation. But again, we are going to be get your major advantages that we require to fulfill your current requirement of your modern communication system. But this system is also basically going to be have some disadvantages. The first thing is the computational complexity. That means when we are going to be design the receiver side, then we require very highly computational system. Due to that, the complexity is going to be increased and cost is going to be increased. So that means we are going to be get their higher complexity in the channel modeling, additional processing cost. So my cost is going to be higher in this particular system. Now, if I am thinking about your specific the MIMO concept, as we already discussed about these two, time diversity and frequency diversity, they require the expensive resources because they are going to be used either WebDMA technology or AMC technologies. Then we have the antenna diversity. Now, if we are going to be seen in detail, then antenna diversity can be classified into the three part. One is known as the spatial diversity, or in some books or some literature, they are going to be say that it is known as the space diversity also. Second one is the polarization diversity, and third one is the pattern diversity. So what do you mean by the spatial diversity? So our task is that the MIMO system is going to be say that we need multiple antennas into their transmitter and multiple antennas into their receivers. So when we are going to be apply, or when we are going to be mount more than one antennas in a single platform, then the separation between these two antennas play a vital role. Normally we know this from the antenna array concept. If we want the lower value of your or minimum value of your mutual coupling, then the separation between two consecutive antennas must be the lambda by 2. So but we want to design the compact systems, and when we are going to be design the compact system, then we are not going to be follow this lambda by 2 rule. In that condition, my distance or my separation with the consecutive antennas is going to be reduced, and when it is going to be reduced, that means the mutual coupling, which we can define as the affecting the performance of the one antenna by the nearby antennas. So this mutual coupling is going to be grow a lot, and that is creating the problem for us. So spatial diversity is going to be useful when we are going to be keep the antenna separation lambda by 2 or higher. In that condition, my system is going to be perform well. Otherwise, it is going to be create the problem. Then what we can do in the next stage, then we have the polarization diversity. So polarization means either we can have the linear polarized antennas or we can have the circular polarized antennas. Okay, if we are talking about the linear polarized, then we can say that either it is going to be the horizontally polarized or vertically polarized. If I am going to be say that I am going to be have the two antennas or one antenna where both are going to be co-located, that means antenna 1 and antenna 2 are having the same position. In that condition, if I can say that my antenna 1 is going to be have the horizontal polarization and antenna 1 is going to be have the vertical polarization. It means both are orthogonal to each other. In that condition, if there is any mutual coupling is going to be happen, that is automatically going to be 0. It means by using this polarization diversity concept, you are going to be make the system concept, and this is not basically going to be affecting the mutual coupling, and it is basically going to be the one of the best solution. And third is the basically pattern diversity. So as we know that the pattern, we can have your directional patterns, we can have the omnidirectional patterns, we can have the monopole kind of the pattern. So if I'm going to be say that normally we are going to be use this MIMO concept for the communication, so we require the directional pattern. So if I'm going to be say that I have two antennas which are co-located. If I'm going to be say that antenna 1 is going to be transmitting the signal, that is the my center position. And if I'm going to be say that antenna 1 is basically going to be transmitting the signal at theta 1 angle, and antenna 2 is going to be transmitting the signal at theta 2 angle. It means the separation between these two direction of maximum radiation is theta 1 plus theta 2, and it is quite large. That means the far field of the antenna 1 is not going to be interact with the far field of antenna 2. In that condition, my mutual coupling is by default is going to be reduced. So how we are going to be place your antennas, how we are going to be use antenna properties to make the system efficient. That means by reducing the or by optimizing the mutual coupling between the antenna elements. Further, we can have two major methodologies how we can operate into your MIMO antenna systems. That is going to be known as the spatial diversity and spatial multiplexing. Spatial diversity means we are transmitting your same information across the independent feeding channel. So here we are going to be have the same data set, and both data is basically simultaneously transmitting from your transmitter 1 and transmitter 2. And it is basically going to be received by the receiver. So we can say that there are two transmitters, so total 4 paths are available. So we can say that here at a time, my receiver is going to be received the 4 signals. For example, for the simplicity. So out of 4, there is a very, very less probability that all the 4 signals are going to be fed together. The most, or we can say that we are going to have your best probability out of 4, at least one signal is going to be having the least faded or least noise. That means that signal is very strong, and that is going to be give your maximum information to us. It means in this manner we are going to be improve the reliability of the system. But when we are going to be use a special multiplexing, in that condition what we are going to be do, we are transmitting your different data bits or different information into your antenna channels. It means here we are basically going to be transmitting the different bits, so we can improve the data rate and link capacity. But here is the problem of the reliability. So now it is the user point of view, or we can say that the application point of view, whether you go for the spatial diversity or spatial multiplexing. If I am going to be consider your two different applications, for example, you have to design the MIMO antenna systems for the defense application. So for the defense application, then even a small or any information that is going to be transmitted from your border to your main data center, that is very, very important for the your Indian, for the defense or for the security point of view of your any country. So in that condition, we need the very reliable system. It means we have to go for your spatial diversity. Now in the second case, let us suppose you are going to be teaching to your 1,000 students simultaneously through your online mode. In that condition, if we are going to be transfer some video content of the lectures to all the 1,000 students, and that video is basically very good quality, when you are going to be transmitting the signal to the special multiplexing, the system transmission is going to be very fast because this is supporting the data rate and better link capacity. Even if some information is going to be lost, still you are able to understand the problem because it is a very higher definition. if something is going to be lost, still the main information you are able to extract. It means it depends mainly onto your application and the user requirement, whether it will go for the spatial diversity or the spatial multiplexing. Now the key parameters of your MIMO antenna, that means the performance parameters of your antenna, how we are going to be check whether it is going to be suitable for your practical systems or not. So if we are going to be go for your single antenna systems, so normally we are going to be use these parameters to characterize our single antenna. Reflection coefficient, that is your S11 parameter, radiation pattern, gain, and radiation efficiency. All these parameters is going to be give you your complete characteristics of your design antennas. But when we go for your MIMO antenna systems, then along with these parameters, we need some more parameter to characterize your complete system. And that is basically given here. Interport isolation or mutual coupling, envelope correlation coefficient, mean effective gain, total active reflection coefficient, and channel capacity loss. So out of these five, these two are very, very important for us. We are more focusing towards these two things. Here I have mentioned two things, interport isolation and mutual coupling. So if I'm talking about your isolation, it means I'm talking about your port-to-port isolation. That means it is the input analysis of your antenna system. When I'm talking about your mutual coupling, that means I'm talking about your far field coupling. That is the far field of your antenna 1 to going to be interacting with the far field of your antenna 2 or vice versa. So during my complete discussion here, we are going to be have two different terms, interport isolation and mutual coupling. Whenever I am talking about your isolation, that means I am talking about your input part of your system, that means port to port isolation. If I am saying about your mutual coupling, that means we are talking about your far field parameters. And we can calculate the ECC either using your mutual coupling, that is your far field term, or we can use your S11 parameter, which is giving your port-to-port isolation. Then remaining three parameters, either they can calculate directly from the ECC or from your S parameters. So that means if you know the top two parameters, then bottom three parameters can be easily calculated. That's why I'm going to be focused on to your first two parameters. And here I have discussed these parameters in somewhat detail. So if I'm going to be talking about the ECC, then we can say that this is the parameter which basically tells us how independent two antennas radiation patterns are. That means if I'm going to be have your antenna 1, which is this one, and antenna 2 here. So how the radiation pattern of antenna 1 is going to be related to your or independent to your antenna 2, that information we can get from your this particular parameter, that is envelope correlation coefficient. This parameter we can calculate from their two different equations. One is based on to their S parameters, another is based on to their radiation pattern. The parameter or the calculation of their ECC based on to their S parameters normally give the information about their port-to-port isolation. And the calculation based on to your far field, that is going to be giving the information about your mutual coupling, that means far field coupling. So in the literature, as we are going to be use the MIMO antenna systems for the communication, which is always for the long distance communication, then the ECC calculation based on to your far field formula are much widely accepted as compared to your S parameters. Now the diversity gain and mean effective gain. So as I told you earlier, if you know the ECC or if you know the S parameters, then remaining parameter, that is diversity gain or mean effective or torque or channel capacity loss, that we can easily calculate it. Similarly, your CCL, that means if you know the S parameters, you can calculate beta 1, beta 2, beta 1, 1 and beta 1, 2, and from here we can calculate the CCL. So that's why we are focusing towards your two parameter, that is your port-to-port isolation or mutual coupling, and then the ECC. Now the benefit of your antenna technology. especially the MIMO. That means it will offer your increased reliability, better data rate, higher channel capacity, and gain of the antenna is going to be increased. Now here I have mentioned three important things. When we are going to be check whether the system is MIMO or not, then here I have mentioned these three input parameters. There must be one port, all the port must have the overlapping impedance bandwidth, and port to port isolation must be better than 12 dB. And ECC value is always less than 0.5. So that I have explained with the help of one simple example. I have taken your two port antenna system. So this is my port 1 and this is my port 2. And from these ports, this is antenna 1 and antenna 2 are excited. So my first condition is that my MIMO antenna system must consist of more than one port. So I have the two ports. My first condition is fulfilled. Now second condition is told me about that the ports associated with MIMO share the same impedance bandwidth. To get the same impedance bandwidth, what will done? I have calculated your S performance or scattering performance. So S11 and S22. So if you see the blue curve and black curve, both are going to be give your almost identical output. That means they are sharing your same input impedance bandwidth. So my second condition is going to be fulfilled. Now third is the isolation values between the ports should be more than 12 degrees. So isolation between port 1 to port 1, that is S21 or S12. So when we check S12 and S21, then you can see it here, the red curve is giving the information, which is better than that -20. So my third condition is going to be here proved here. Now I have checked your ECC value, which is must be less than 0.5. So based on those parameters, I have calculated the ECC, and within the desired frequency range, this ECC value is approximate near to the 0, and our requirement is 0.5. So we can say that we are getting the better ECC value. Final, that is not always true, but it can be very useful for us. We require the specially separated radiation pattern. The reason is that we want the better ECC, and ECC is giving the information about how two antennas radiation patterns are correlated or independent. It means if my antenna 1 and antenna 2 are radiating into their two different way, then we can say that we will get their better ECC. So here you can see that, let us suppose this is your X direction and this is Y direction. So port 2 is this way and port 1 is this way. So both antennas are going to have their different field configuration, and due to that their far field pattern is also going to be orthogonal to each other. So it means the mutual coupling is going to be very good in that condition. So this system is going to be very effective system for your MIMO antenna system. So whenever you are going to be design, you focus on to this particular part of your system design. Now the role of your DR, that is electrons or antennas into your MIMO antenna systems. So if you see the current state of art, these two antennas are widely explored by the researchers. One is the microstrip patch antenna, another one is the dielectric resonator antennas. And this is the antenna which is most widely used, more versatile. And if you see that today's any compact devices, everywhere you can find this antenna. But this antenna is going to be have the metallic structures, and that metallic structures are responsible for the radiation. So we have ground plane, then we have substrate, and at top we are going to be have their patch over. This patch, which is metal in nature, that is going to be start radiating. So this metal is basically responsible for the radiation in microstrip antennas. But when we are going to be increase the frequency of operation, then this metal is suffering from their conductor loss as well as the surface wave loss. And the surface wave loss is going to be more severe when we are going to go to your millimeter wave range. So due to that, what will happen? These losses are going to be very increased, and it is going to be affecting the efficiency of the antenna and the bandwidth. So we can say that at higher frequency region, this antenna is going to be have the very low efficiency and restricted bandwidth. So how we are going to be solve it? That is the answer, that is the dielectric resonator antenna. And the dielectric resonator antennas, we are going to be use a piece of ceramics that is a dielectric in nature, and we are going to be feed this ceramics from the any feeding mechanism, and due to that this antenna is basically going to be start radiating. So here we don't have any metallic structure. That means only the dielectric. And dielectric losses by default, if we are going to be choose a material in such a way, it can be very, very minimum. So here what will happen? We don't have any conductor losses or surface wave losses, only the dielectric losses, which is very, very small. That means it is going to be offered your better radiation efficiency, better bandwidth, diversified pattern, support feeding method, and flexibility in design. So this is the basically going to be one substitute of your microstrip patch antenna. Now we are going to be see some history about your dielectric antennas. So we can see that in 1939, the first time the concept of dielectric resonator is given by the R.D. Richman. He is the person who mathematically apply the theory and say that this can be possible. But at that time we don't have the such kind of their materials available into the market so that he can prove this theory. So it will take almost more than 21 years. This concept is going to be realized in the practical manner. And then they are going to be used as an oscillator and filters into their microwave industries. And after almost 23 years, Professor Long is basically do the wonderful job to explore can we use this electric resonator as an antenna. So, and when he basically focus on this one and then find it can be possible, then he termed this dielectric resonator working as an antenna. So the name will come into the picture, dielectric resonator antenna. If I am going to be define what is DRA, so we can say that it is a resonant antenna fabricated from your low loss ceramic materials. That means to design this antenna, we need the ceramic materials. And its resonant frequency is function of the size, shape, and material permittivity. That means if you want to design the DRA, you need the material, and its size and shape is going to be defined the resonant frequencies. So this part I have already explained. Because of your efficiency issue into your microstrip patch antenna, we need the DR, and that DR is going to be get these important things for us. If I'm talking about your shape, then we can say that these three are the fundamental shapes. Hemispherical, this one, then we are going to have the cylindrical and rectangular. These are the three fundamental shapes. Other than this, they are going to be known as your deformed shape. This can be triangular, this can be cone, this can be toroidal shape, or any kind of their structures. Now, if I'm going to be compare all the three shapes of your DR, we know that the resonant frequency of your DRA is going to be function of your shape, that is SH, the size, that is SZ, and the material permittivity. Now, if I'm going to be say that I have fixed the hemispherical, that means I fix the shape. After that, I fix the material, that means that is also fixed. Then we can control the resonant frequency due to the size. And this is basically hemispherical DRA, that means only the diameter or radiation is basically possible to control the resonant frequency. So technically we can say that we don't have any parameter to control the resonant frequency. It is going to be fixed. So that's why it is going to be said that we don't have any degree of freedom to control this one. But when we are moving towards the cylindrical DR, other than the radius or diameter of the DR, we have the height. So we are going to be get your flexibility. Either you can change the radius, either you can change the height. Even your shape, that is your shape and epsilon are going to be fixed. So that means it is can offer your better degree of freedom. So we can say that 1 degree of freedom. If we are moving towards your rectangular one, so we have your W, we have the L, and we have the H. So here we are going to have the 3 parameters. That means it will offer your 2 degree of freedom. So if you are thinking about your engineers and in engineer's point of view, then rectangular DR is going to be your most flexible or most flexibility is providing by the rectangular DRA to the antenna engineers. But if you see the literature, then this is the DR which is widely explored because its designing is easy, it is commercially viable, and the model analysis of these antennas are widely available. As we know that these are the resonant antennas, so we have these three kind of their fundamental modes: T mode, TM mode, and HEM modes. And in the DR, each mode is going to be provide their unique far field pattern. That's why the model analysis is very, very important into your DR. So let us suppose if I'm talking about the cylindrical DR, so T01 delta is the fundamental mode, TM01 delta is the fundamental mode, and these are the fundamental modes. If we are going to be have TM01 delta, that is by define, if we are going to be excite this TM01 delta mode, it is going to be give you your monopole kind of the radiation pattern. If you go for the T01 delta mode, it is going to be give you the broadside radiation pattern. So by knowing the modes, you can decide what kind of the radiation pattern you are going to be get. So that is the reason why the model analysis is going to be important. Similarly, we have the rectangular DR. So T111 mode is the most fundamental modes, and then they are going to be have their higher order modes. Now, how to basically energize these DR? So for that purpose, we can use the different kind of their feeding mechanism: coaxial one, microstrip alignment, and aperture feeding. So that is a well known, and they are basically going to be used into their microstrip antennas also, and they are applicable here also. I will use any one into my coming discussion. Now, the important point is how to improve the performance of my antennas. That is the measure is the isolation improvement. So in the literature, these 5 techniques are available to improve the performance of my antennas. The first one is your generation of their orthogonal modes. Give me a minute first. So here we are going to have their 5 important techniques to improve the performance of their MIMO antennas. So first one is the generation of their orthogonal modes. So if you see here, let us suppose this is your X direction and this is your Y direction. So here I have used your 2DR. So port 1 is your X directed and port 2 is the Y directed. So we can say that the field which are going to be generated by your DR1 and DR2 both are going to be orthogonal to each other. And if field are the orthogonal to each other, that means their interaction is going to be 0. It means we are going to be get no mutual coupling. That means my antenna performance is going to be improved. So this is the most widely used and most easy technique. But in many cases, this concept is not available. Then we are going to have their excitation of their degenerated modes. So if we have degenerated modes, means the modes which are going to be have their same resonant frequencies. But here, this is the one of the best technique which makes the system compact. But the problem is that to generate the degenerated modes, that is a difficult task into their DRA. If anyone basically wants to work onto their MIMO DRS, then this is the area where you can work. You can find the different techniques to generate the degenerated modes, and then you can apply onto their MIMO systems. And that system is going to be very, very compact, and it is going to be give your better understanding and better performance. Second or third condition or third technique is the defective ground structure, that is a DGS structures. This is very useful and most widely explored, but the problem is that it is going to be affecting the radiation characteristics of your antenna. So whenever you are going to be apply the DGS concept, you continuously monitor your radiation performance. Now we are going to be have their decoupling structures. Here we are going to use some additional structure to basically improve the isolation or mutual coupling of their antenna systems. And finally, we are going to be have their meta surfaces, frequency sensitive surfaces or EBGs, where we can basically going to be improve the isolation or mutual coupling. So here, these are the area where people are working nowadays. But the problem with this system is that the placement of the EBG structures or metasurfaces or frequencies, because they are very sensitive. Second thing is that they are making the system bulky. So if you want to design the compact system, then you cannot use these things. But if you don't want the compactness, then these systems are going to give you the better results. Now we will discuss our some examples that we have recently basically published. So here what we have done, we are basically going to be using one kind of your partial reflecting surfaces that is going to be used to basically squinting or basically diverting the antenna radiation pattern in one direction, and along with that it is going to be improve the gain of their MIMO antenna system. So we have used your 3-port antenna, antenna 1, antenna 2, antenna 3. In the between of your DRAs, we have placed your absorbers, and at the top of your this structure we have placed your one anisotropic PRS, that is your partial reflecting surface. So let us first discuss about your what this antenna is, that how we are going to be viewed. What we have done, initially we have designed the 3-port antenna system. Then by incorporating the basically, when we are going to be see that this is the MIMO antenna system, so to improve the isolation and other performance, we are using your PRS system along with your metamaterial absorbers, and by incorporating these two, we are going to get our final proposed structures. So now the discussion about your partial reflecting surfaces. So if we are going to be discuss the PRS, it is the basically 2D surface that partially reflecting electromagnetic waves while allowing the remaining wave pass through the or propagate into the certain direction. It relies on techniques of multiple reflections in a cavity to improve the performance of antenna structure and work on the principle of Fabry-Perot cavities. Normally, it is act as a superstrate, and consists of the periodic cells along an axis. So here we can use the PRS in two different modes. The first mode is the gain enhancement. The second mode is the beam squinting. If you want the gain enhancement, then condition is that all the PRS must be identical. It means whatever the unit cell we are going to be design, that unit cell must be repeating in a manner. That means all the unit cells are going to be have the same. And due to this nature of your PRS, the waves basically going to be emanating from them and combining with the same phase. And due to that, it will form the directional beam. That means the gain is going to be improved. For beam squinting, we need the gradual variation in the dimensions of the unit cell. That means my dimensions of the unit cell is gradually decreasing or increasing. And when we are going to be do this, in that condition, the waves are going to be combined with certain phase differences, and due to that, the beam tilting or beam squinting is basically comes into the picture here. So when we are going to be focused onto this concept, then we got that either the PRS has been used for gain enhancement or beam squinting. So now here we have tried, is it possible can we design some kind of their PRS which can improve the gain along with the providing the beam tilting. So that is the uniqueness in this particular structure. So now we are going to be discuss one by one. So we first design the 3-port antenna, and that antenna is going to be excited by your conformal strips, and we are going to be up your full ground plane. So we got your antenna which is going to be operated from 5.2 to 5.7 gigahertz, but we want to improve our isolation. And what we have done, we have designed our PRS. So that is my proposed PRS. This is the top view, this is the bottom view. So if you see the bottom view are going to be have your same dimension, that is your straight. But if you see the top view, in the top view, we are going to be have PRS1, PRS3 and PRS2. So if you see PRS1 and PRS3, they are basically identical but complementary to each other. If you see here, we are going to be the highest dimension. In the PRS3, this is going to be your here. So your PRS dimensions are gradually decreasing here and gradually decreasing here. That means both are complementary to each other. If you see the PRS2, then you can see that all the center PRS are going to be have their same dimensions. Okay. Now you can see it here. So if we are going to be check the PRS here, so they are almost constant, but there is a gradual variations. That means the PRS1 and PRS3 are gradually varied, and that is going to be the constant. So it means the PRS1 and PRS3 is going to be useful for your beam squinting or beam tilting, but PRS2 is going to be the broadside gain. That means gain improvement. So same we have checked. Initially, we have the 3-port antenna and we are not providing any kind of your PRS system. So you can say that all the 3 antennas are going to be radiate into your positive Z direction. And due to that, there will be the mutual coupling between them. But when we are going to be place the PRS, you can see that this is the PRS on the top of DR3, DR2 and DR1. Then you can see that the DR3, the direction of their maximum radiation is going to be tilted by their plus 30 degree. And similarly, DR1 is minus 30 degree. So here we can say that thus angular separation between the your DR2 and DR3 far fields are going to be increased by the 30 degree. Similarly, here are going to be increased by the plus 30 degree. That means now by squinting the wave into the two opposite directions, we are going to be improve the mutual coupling here. And if you see the port 2, in the port 2 case, if you can compare the top one and bottom one, so you can see that my port 2 is basically going to be much more confined. It means it is going to be made as a pencil wave. That means the antenna gain is going to be greater. So you can see it here, there is a significant change into your gain, that is around your 1.5 dB. After this, for further improvement, we have designed your absorber, and that is basically my absorber performance. We have designed and we have go for the your ADS as well as HFSS, and from there we can say that the real part of permittivity and permittivity are equated for 100% absorbance and maximum isolation. After that, we have placed at the center position and then we checked it. So when we are going to be see that, we can say that our performance are going to be well matched with the experimental, and we got plus minus 30 degree tilt into the your port 1 and port 3 and better isolation by applying the your these metamaterial absorbers by the your 16 dB. Then we have calculated the your ECC and DZ, and which is the your well limit that is specified for the system. Now we know that your antenna polarization. So polarization, we can say that it is the orientation of electric field vector in a particular direction with change in time. So in broad sense, we can categorize into the linear and circular manner. So for the linear polarized antenna, these are the two conditions which we need to discuss. And for circular, there are 3 conditions. So if you want to the linear polarization, then we required only one electric field must be present, and if 2 are present, then they must be the 180 degree phase difference. If these conditions are going to be met, then we can say that your antenna is the linearly polarized. But if you are talking about your circular polarization, then these 3 conditions must be true. The first thing is that 2 orthogonal linear component, and these components must have the same magnitude, and they are going to be separated by the 90 degree phase difference. So when we are going to be follow these conditions, then we are able to generate the circular polarization. So the circular polarization, either we can have the right hand circular polarization or left hand circular polarization. Similarly, in the linear, horizontal, vertical and slant, it depends upon the application to application which polarization you are going to be used. But our target is that we want to see into your MIMO antenna systems. So this circularly polarization is basically going to be make the system independent upon to your position or variation. Now we already discussed about these 3 diversities: space, polarization and pattern. Now we are focusing on to why we go for this antenna diversity. So to improve the isolation, the design suggestion is to maintain the EM field with less coupling. So if I am going to be the space coupling, that means the phase delay between elements of 2 different points in space can reduce the EM field coupling. In polarization, the orthogonal polarization can suppress the EM field. In pattern, the different radiation pattern can diminish the E-field coupling. That means anyone you are going to be used to basically improve the overall performance of your system. So here I'm going to be discuss about this problem where we are going to be use all the three antenna diversities in a single system. And we are not basically going to be use any additional structure to get your better diversity. So here you can see that we are using your back-to-back arrangement, and we are using two different designs in a same structure. First design is showing by your green color, second design is shown by your blue color. That means these are the two different DR which we are using to make this kind of their structures. So what is the design approach? A design approach is that first we have designed a microstrip slot based CPDRA, and second I have designed a conformal open loop CPDRA. And after that we converted these two different DRs, circularly polarized DRs, into their MIMO configuration with the different approaches. First I have taken the same antennas into their different positions. Then I have basically made the combination of both. So by changing these different combinations, we got our final combination that is going to be provide the optimum diversity performance. And then we have tested it and we got our final results. So now we will see here the one by one. So first one is by the microstrip slot feed CPDR. Second one is the conformal loop antenna. So here you can see that we have used a very unique kind of their slot and the microstrip feed line, which is going to be have their lambda by 4 quarter wave, and the T-shape arrangement here that is going to be used for the impedance matching. And here we have used your conformal loop that is going to be create a circular polarization. Now let us see the one by one. So this is my first structure. So initially we are going to be have the cylindrical DR. It is going to be excited by your one circular slot. Further, we are going to be increase these 4 U-shaped slots, and then we have changed the dimensions of the U-shaped slots, and finally we are going to be convert this microstrip line into your quarter wave transformer along with your T-shape. So now when we are going to be check your reflection coefficient and performance, then you can see that 1, 2, 3 are not basically going to be your better response. The final one is going to be better response. But if you compare from 3 to 4, they are basically going to be give their better impedance matching. So that's why we are going to use this concept for better impedance matching. It will improve your S11 performance. From here to here, there will not any change into your CP that is given by their XL ratio. So you can see that third and fourth are going to be give their similar results. But from third to fourth, we are going to be get their better S11 performance. Now, the second structure that we have the conformal open loop. Initially, we have the cylindrical DR that is excited by the conformal strip, and then we have incorporated the open loop. So you can see that initially we don't have your circular polarization, but when we incorporated the conformal loop, we got the circular polarization. Now we are putting these two antennas into your MIMO configuration. Initially, I have choose the microstrip slot based and circular DRA that is going to be into your system 1. And when we have designed, then we find out that the isolation is going to be very poor. So that means the system cannot be used. Otherwise, we have to incorporate some different coupling mechanism. Then we have shifted toward your second antenna design and we have placed into this manner. Then we find again the isolation is higher, so we cannot use it. Then we have combined both antennas. So on the bottom side I have used one, on the top side I have used one. Again, it is improved with respect to your previous two systems, but again it is not going to give the better result. Finally, we have got another approach where we have placed the diagonally, and when we are going to be do it, then we can find all the isolation values are going to be less than 15 dB. So here we are not going to be apply any external mechanism here. By placement of the DR in such a manner, we are going to be get it this one. That is a uniqueness in this structure. That means first thing is that to get the circular polarization, and then to get your better mutual coupling without any applying any extra kind of your isolation improvement technique. This is the my fabricated design, and then we have tested and we find that our simulated results are well matched with your experimental results. Then the axial ratio and gain response, and finally the ECC and DG and MEG performance. Now we are going to be discuss about your one new scheme that we have. Basically, I can say that first time we have used into your dielectric resonator antenna concept, that is known as your decoupling metallic sheets. So why we are going to be use a DMS? The concept is that to contract your original coupling. How? That we are going to be discuss. We know that EM waves can be perturbed, constrained or blocked by the help of metallic body. This concept is very well known in the beginning, and I have explored, or we have explored the same concept by noon, and then we are going to be say that is known as your decoupling metallic sheets. So it means we can use the metallic bodies to influence the EM energy distribution. That means we can use to control the coupling. What we have done? We have taken this concept. Here we have used a very compact antenna, very compact antenna, and this concept we have designed for the 28 gigahertz 5G band. What we have done? We have taken a cylindrical or rectangular DR, and that DR we are basically going to be excited by your rectangular slot, and both are basically same structure. The only thing is that the way of excitation. Here we are going to be used in this manner, here we are going to be use the complementary manner. So we are going to be term as a two different things. One is the your E plane DR, E plane coupling, or another H plane coupling based on to their field distribution. Other than that, here we are using two metallic sheets that is going to be embedded within this structure. Similarly, here the two metallic sheets. Clear? So the performance we got this one and LP, this one and LP. So both are comparable and they are going to be give the good results. Now we will see one by one. So initially what we have done, we have taken a DR, rectangular DR, and here we have placed two metallic sheets that you can see it here. These two metallic sheets. You can check it here, and at the bottom we are going to be use this rectangular strip to basically going to be excited. And these are the dimensions, which is very compact structure. You can see that the maximum dimension is 11 mm by 16 mm. That is 1 centimeter by 1.5 centimeter maximum. So now these are the design analysis, or we can say that your evolution of your proposed design. Initially what we have done, we have taken the rectangular DR, only this single rectangular DR. You can check it, this is only one piece of the DR, but we are going to be have your port 1 and port 2, and we are using the aperture coupling here. So my configuration 1, if we are going to be see, then it is going to be get in this one. Then I have applied the configuration 2, where we are going to be introduce a metallic strip at your center position. So you can check it here. Initially we are going to be have your this one, my isolation, and when by introducing your one metallic sheets, I got this one that is going to be improved. And when we are going to be put the two metallic sheets, then my isolation is going to be improved a lot. It means by applying, by inserting the metallic sheet into your structure, we are able to improve the isolation into your system. Okay, and this is the DR, so that's why we have checked what the mode we are going to be excited here, which is the fundamental mode, that is TE111 mode. From this analysis, we got that we are able to improve the isolation of the system. Now we want to see why we are going to be get this one. So initially what will happen when we are not going to be have any metallic sheets, and when we see the field distribution, then we find that due to the port 1, there are some mutual coupling into their port 2. And the same thing we have checked with the surface current distribution. We are energizing port 1 and my port 2 is basically ideal. That means we have put the 50 ohm short here, 50 ohm load here. But due to the surface current distribution, my feed line 2 is basically going to be excited. and then it is going to be excite my DR. Due to that, my mutual coupling is high. But when we place the two metallic sheets, then you can see that here and here there is almost zero mutual coupling. That means my metal sheets are basically going to be creating the restrictions of their surface current distribution to reach at the port 2. And that is the reason why my mutual coupling is going to be improved a lot. Then we have fabricated and tested, and we got the better results in the both conditions. Now, in the second approach, I have placed the metallic sheet at your side by side. So here the metallic sheets are there. Then we checked initially we don't have any metallic sheet, and then we place the two metallic sheets. And when we see that, you can check there is a lot of improvement into your isolation. Second thing, when we are going to be do this arrangement, then we find that we are able to generate the higher order modes. And due to higher order modes, my bandwidth is going to be improved. So we got the information why bandwidth is going to be improved. And then we have to explain it why the isolation is going to be improved. Initially, when we are not going to be have the any metallic sheets, then you can see that when we are going to be energize feed line 1, it is going to be affect the your feed line 2, and that is same shown here. We are energizing feed line 1. This red line is showing the your highest density of your surface current, and due to that the feed line 2 is going to be excited. This is the reason we are going to be have your poor mutual coupling. But when we are going to be include the two metallic sheets, then you can see that here there is no sign of your induced current or surface current here, and due to that there will not be any kind of your excitation. So that means my metallic sheets are basically going to be working as a isolation improvement here. Then we have fabricated and tested our results, and we find that that is well matched and it is very improved version. Then we have compared our both structures into the same region of your field, and we find we are going to be get your better results. So as a conclusion, we can say that we have discussed three different designs. In the first case, we have employing the your PRS concept for the beam squinting as well as the basically your gain improvement. In second condition, I am using the your circular polarization, circularly polarized MIMO DRA, and with the help of the your pattern and polarization diversity, we are improving the your isolation or overall performance. In the third condition, we are exploiting the metal sheet concept, and we have apply onto the your 5G MIMO DRAs where we can achieve the highest compactness. But if we are going to be talking about your future scopes, then we can say that there is a huge possibility into the your 5G. That means into their millimeter wave. But as we need the very good materials to design these antennas, that is a bottleneck. So if people can focus on this one. So these are some references. And if you have any question, then please let me know. I'm happy to answer.
So there are some questions in chat box. We will take that first.
Yes, please.
So the first question is DRAs. Just a second. What are the materials used for DRA?
So in the beginning, I told that you can use a ceramic materials, and the property is that the dielectric constant or relative permittivity of your material lie between to the your 6 to 40, and they are very low loss in the range of your 10 to the power minus 4 or better. So any ceramic material which are lying in this range, you can use for the DRA fabrication and testing.
So which software is preferred for simulating DRA?
In which you are comfortable. I am using the HFSS and CST both. So it is up to you whether you go for HFSS or you go for CST or any other kind of the software like EM Pro, FACO. It depends. in which you are comfortable, you can go for it.
DRAs are 3D structures,
Yes, these
are
are
they?
3D structures.
Am I audible?
Yes, Aarti, you're audible.
So next question is, are DRAs the 3D structures?
Yes, I told DRAs are the 3D structures.
And how do we test DRA? How many ports in VNA?
No, that is not the right question. It depends how many ports DRA you want to design for MIMO application. 2 ports, 4 port, or it is up to you how many ports you are going to be take. Normally, when we are going to be test our MIMO antennas, we are testing at one port and remaining ports are basically going to be matched. In that manner, first you test this first port, then remaining ports are going to be matched, then you go for the second port, and then remaining ports are going to be matched. In that manner, one by one, you are going to be test your antenna. This is the procedure to get your performance of your MIMO antennas.
How to identify the exact location of MIMO port,
Now, there is no MIMO port.
of the
MIMO
feed
is
for
the
the MIMO
quantity.
antennas?
Uh-huh. Basically, it depends what kind of your mode you want to excite. So, for let us suppose if I am going to be go for the TM01 delta mode into the cylindrical DR. So, for TM01 delta modes, I have shown into the picture that you have to put the probe at the center position of the cylindrical DR, so that the necessary boundary conditions are going to be matched. That is going to be create the TM01 delta mode into your cylindrical DR. So there is a one very good book are available. Good books are available on the DRA. One is written by their KM Luke and Leong. Another one is Aldo Pitosa. And you can use those books where they have discussed in very detail where we are going to be, how we are going to be excite the TM10 delta mode or TE mode or HEM mode. And based on that, you are going to be design your own antennas.
Any other questions from participants? You can unmute yourself and ask, or you can post it in chat box. How to identify the excitation modes of MIMO on HFFS? HFS
You
system.
have to check the basically your electric field distribution within the DR. And based on that electric field distribution, you can identify what the rotation they are going to be take. I have shown some figures how the TM01 delta look like, how the TE011 delta look like, how the HEM11 delta look like. So whatever the books I have told you that they have already defined what are the different type of their modes are going to be have the different distributions. So you can resemble what you are going to be get and what is the ideal should be that. And based on that, you can check whether it is a TM01 delta mode or TM mode or HEM mode.
Design equations for DRA? Nandini
Whatever the
ma'am?
two equations I have, two books, the name I have given to you, in that books, the complete design equations are there. So you can refer. One is the Handbook of Dielectric Resonator Antennas by Aldo Pitosa. Another book, the Dielectric Resonator Antennas by KM Luke and Leong. These both books are going to be have their all the necessary mathematical equations. With the help of that, you can design your antennas.
Any other questions, participants? I guess there are no questions further. We have shared session 1 and session 2, both the feedback links. Apart from that, any other questions? Okay. So thank you, sir, for giving your in-depth insights on MIMO techniques and antennas, basics of dielectric antennas, different resonant antennas, their working modes, antenna design evolutions, and their comparisons. We are very thankful on behalf of everyone here. We are truly grateful for your time and efforts, sir. Thank you so much.
Okay, thank you. Thank you very much for inviting me. Thank you, one.
Thank you, sir, for this session.
Photograph एक
Before we wrap up, there is an announcement. We need for after every session we will be clicking one photograph. Okay, and one more thing, we will be sharing the attendance at there will
Excellent
be
session,
an
sir.
attendance at feedback form for every session, and that will be shared after at the end of every session. Okay, today we have already shared both the session feedback form. Both of them are right there in the chat box.
Okay, so we'll take photograph.
Yes, please turn on your cameras so that we can take one photograph.
So 1810.
Yes, done.
Done?
Yes, yes. Done.
Okay. Thank you, sir. Thank you, madam. And thank you
Thank
all the
you. Thank you, ma'am.
participants for your contribution.
Nice session. Thank you.
Thank you.
Thank you. Have a great time. Good night.
Thank you very much.
All the participants, please fill the feedback form for the session 1 and session 2. The
Feedback
link,
form will
please.
session
not be
two.
shared in
Please,
WhatsApp group. So kindly
please
fill up
post.
the feedback form for session 1 and session 2.
People are asking for session 2 feedback link. Please share it again.
Chintan, are you there?
I will share. I will copy and paste.
Okay.
Because somewhere
Yes, ma'am. Yes.
confusion is
Yes,
there.
yes.
Session 1 or session 2. Because someone is saying that already.
Ma'am, I have already shared both the links again. If
Who
they
have,
want, I will share them.
who have
Yeah, yeah.
responded, please do not respond again.
We have shared the feedback link again. Kindly fill it up for session 1 and session 2 both.
We will wait for 5 minutes, madam.
Ma'am, we will be providing all the PPTs and everything later, right?
Chintan, someone is saying that link is not opening. Hariharan sir is telling. Hariharan sir, are you there?
No, ma'am. Link is working, ma'am.
Link is working, I guess.
हाँ.
It is working, madam.
चैट बॉक्स में मैम उनको बोलो चैट यहाँ पे ही चेक करने के लिए. मीट लिंक में ही मैंने शेयर किया.
We'll give 5 minutes, madam, now, after this.
Yes, afterwards, for
Huh?
5 minutes
Then we'll
only.
wind up after 5 minutes. I think Aarti and Manisha other can leave.
Yes, yes,
Huh?
yes.
Yeah. We'll wait for 5 minutes and then we will.
Yes, Aarti, Manisha, you can leave. Thank you.
We can leave.
The recording is to be ended, right?
Anuradha, yes.
Yeah.
Manisha is there. Manisha, Anuradha is there.
Yes. Okay, ma'am. Can we leave?
Yes, yes.
Thank you.
Thank you, madam.
Thank you. Thank you,
Bye
everyone.
bye. Good night.
Thank you, everyone. Good night.
To books suggested by